Thank you, Don. So it's a real fun time to be playing with hardware these days. And since the topic of this conference is agents, I thought I would give you an example of an agent that one of our folks in our Toronto AI lab built. It's called Agentic, and it's basically a second-year graduate student doing computational chemistry. So if you have a question like what is the activation energy of caffeine, caffeine being very important to me this morning, you can give it this question, and you see the hierarchy of agents there, that little tree structure. Each of them, is an LLM with some state that's been, through a combination of fine-tuning and a prompt, given a task. So it will figure out how to generate the geometry of the molecule, optimize the geometry, submit a Slurm job to run a densital functional theory computation to actually do the calculation, and then post-process that and ultimately give you the answer. And this is an example of what you can do, with agents. So let's zoom in a little bit. And each one of those agents in the tree, the heavy work is done with the LLM, possibly with a chain of thought or tree of thought to give it some reasoning performance. But it's also very effective because it has tools, right? So the tools are, running the quantum chemistry simulation or doing a geometry optimization. But a tool can be as simple as a calculator. If you want a LLM to do some calculations for you, you're better off with like a 1 billion parameter model attached to a calculator than you are with a trillion parameter model trying to do that calculation just with the language. And so it's a very powerful thing to take that LLM and couple it with a little bit of internal state and memory and a policy and a bunch of tools that can be accessed. But this session is about infrastructure. Let's talk about what it takes to run one of these agentic models. And I'll start with some motivation. Deep learning really takes three things. It requires algorithms, as illustrated by the figure from the AlexNet paper on the bottom here. It requires data, as illustrated by the ImageNet photo on the upper right. And it requires hardware. You can think of this as sort of air, fuel, and spark, right? Once you have the air and the fuel, you need the spark to ignite it. So the thing that was here first, think of this as the air, were the algorithms. Deep neural networks, convolutional neural networks, training them with stochastic gradient descent and backpropagation were all known in the 1980s. In fact, I took a course when I was a graduate student at Caltech from John Hopfield in 1984, where I learned all this stuff. I got to build these neat little models, have them do really toy problems, and I concluded that this will never be practical because it requires so much more compute than we have today. Well, things have come a long way since 1984. We have a lot more compute, but the algorithms were around in the 1980s. The data started coming around in the early 2000s with the Pascal data set and then the ImageNet data set. And so they were around still for roughly a decade before things really took off. The spark that ignited that air and the fuel that were sort of sitting around waiting for the last missing ingredient was hardware that was fast enough to train a reasonable sized model on a reasonable sized data set in a reasonable amount of time. In this case, the AlexNet model on the ImageNet data set in roughly 2 weeks. And that was done with a pair of our Fermi generation GPUs. And then things really took off. And the way they took off is a factor of 10 million over the last decade in terms of the number of floating point operations required to train a state-of-the-art model. And there are really two very distinct trends. I could have drawn one line through the whole thing. You can draw a line through any set of points. But there are really two distinct trends here. During sort of the era of people building vision models, which is sort of the blue line here, starting with AlexNet and running up through ResNet and things like that, the growth rate was about 3 times per year. And even that is a pretty heavy lift. But since the Attention is All You Need paper came out in 2017 and people started building transformer-based models, the slope has been 16x per year, which is very, very tough to keep up with. And so as the people who build the bulk of the hardware that's used to train these models, we feel a big responsibility because in many ways the advancement of models is gated by the performance of hardware available to train them. And we feel a lot of pressure each generation to increase the performance both of a single GPU and the ability to scale up to more GPUs to meet that. So how did we do that? So this plot sort of shows the evolution of NVIDIA hardware for running deep learning over basically the last 12 years. And Blackwell is up enough that I didn't want to distort the rest of the graph by putting it on there, but it's up at 20,000 equivalent tera operations per second. We started with the bottom left corner here, is our Kepler generation. This is actually the GPU after the one that was used to train AlexNet. That was the Fermi generation. Each GPU is named after a scientist. And Kepler wasn't designed to do AI. When we really made the decisions and locked down what was going to be in Kepler, we were focused on computer graphics, which needs 32-bit floating point, and scientific computing, which needs 64-bit floating point. And both of those are vast overkill for deep learning. But I kicked off our first project, actually before the Keplers were around. I kicked it off in late 2010 to basically replicate Andrew Ng's experiment finding cats on the internet on GPUs. And in doing that, we really convinced ourselves AI was going to be a big thing. We needed to start putting features into our GPUs for AI. So in the next generation, it was too late to catch Kepler at that point, but the next generation we put in support for 16-bit floating point, and also put in dot product instructions, and I'll explain a little bit why that's important later. And so in the Maxwell and Pascal generation, it's really the same core GPU architecture. We had FP16. The next big jump happened in the Volta generation, where we realized that we really had to start amortizing out more of the cost of an instruction. Dot product was an improvement over floating multiply add, but matrix multiply was an even bigger improvement. So we put matrix multiply instructions into Volta. The HMMA, half precision matrix multiply accumulate instruction, multiplies two FP16 4x4 matrices together and sums the result into an FP32 matrix. The marketing people didn't like HMMA, so they called it tensor core. And then in the Turing generation, we had the integer matrix multiply accumulate instruction. In the Ampere generation, we added sparsity, and in Hopper, we added FP8 and in Blackwell, FP4. So where does the performance come from? And it's interesting because during the period of time when everybody was using CPUs, the bulk of the performance came from process technology. Moore's law was really about process technology, allowing you to build a faster CPU, basically doubling the performance every couple years. That has been dead for probably close to 20 years. And really, it died with the end of Dennard scaling, the constant field scaling of devices in 2005, when we stopped scaling supply voltage with gate length. And so over this entire period of time, from Kepler through Blackwell, what we've gotten from process technology is a factor of about 3x out of a total of about 4,000x. So where does the rest of that come from? Well, the single biggest gain in performance has come from number representation. So starting with FP32 in the Kepler generation and going down to FP4 in Blackwell has given us a factor of 32x. And to go to the int8 in FP8 and Hopper has given us a factor of 16x. And it's quadratic because when you do these operations, the dominant operation is multiply, and when you do a multiply, think about doing long multiplication by hand, you generate an array of partial products. So you have a number of partial products that's quadratic in the number of bits in the operands, and so the energy of the multiplies goes quadratically. The next biggest gain has been coming up with complex instructions. I'm actually going to jump ahead a slide, and then hopefully I'll be able to back up. If you look at how much energy it takes to do, and I've normalized all this to 45 nanometers to sort of not leak any information. Our energy numbers now are like an order of magnitude smaller than these. But anyway, to do a half precision floating multiply add, an FP16 floating multiply add in 45 nanometers takes about 1.5 picojoules of energy. But to fetch that instruction, decode it, fetch the operands, and store the results takes about 30 picojoules of energy. So the overhead is 2,000%. You're spending 20 times as much energy on overhead than you are doing the operation, kind of like a big corporation. If instead of doing a single floating multiply add, you do a dot product, now instead of doing 2 arithmetic operations, you're doing 8, right? So I've reduced that overhead by amortizing it from 20x to 5x. And continuing this, when you do the matrix multiply instructions, with the half precision matrix multiply, the overhead is now just 20%, 22%, and with the integer matrix multiply instruction, that's actually doing 1,024 operations on a single instruction, it's down to 16%. And in today's GPUs, that number's around 11%. So we've worked really hard to amortize the cost of instruction overhead out. And if you look at that over this chart of where the gains have come from, that's given about 12.5x right? Not as big as the 32x from number representation, but still a very, very big factor. You multiply those together, and that's almost a 400x improvement. Then comes process technology. That's given us a 3x from Kepler through Blackwell, and that's going from 28 nanometers down to 4 nanometers. And if you look at this chart, it's actually color-coded. It's hard for me on the monitor to see, but the black is 28 nanometers, the green is 16 nanometers, Ampere is I'm trying to remember, 7, and then we have 5 and 4. And so, going all the way from 28 nanometers to 4 nanometers, only a 3x gain in energy per operation. Going to the Ampere generation, we introduced sparsity, that we can basically, as long as you insist that out of every 4 elements of your matrix, no more than 2 of them are non-zero, we have very efficient implementation of structured sparsity, and that gives us a 2x boost in performance. And then on Blackwell, it's cheating a little bit, but it's really 2 GPUs. We have 2 reticle limited die that are on one package that we call 1 GPU. And so we essentially doubled the performance by doing that. It did not improve the performance per watt, though. So I talked about complex instructions. The other thing we had to do, so we basically got essentially 1,000x of that 10 million that we needed to support the growth in model demand for training from making the GPUs better. The other 10,000-fold comes from using more GPUs. And there are several axes to the parallelism that we use here. The first split is between data parallelism, which is sort of into the page on this chart, and model parallelism, which is the x and y axes on this chart. Data parallelism is easy. You take your training data set and you break it up into batches, and you dole these batches out to different groups of GPUs, and they basically operate independently, so it requires very little communication to do this, and relatively modest synchronization overhead to do this. And then when you finish a batch, everybody sends their results together, so you can sort of combine the difference in weights from the one batch to the next. So everybody learns not just from their batch, but from everybody else's batch as well, and then you do the next set of batches. So data parallelism is easy. What's harder, but which you need to do also these days, is model parallelism. And model parallelism here we split across 2 axes as well. The first is pipeline parallelism, which is the y-axis here. So if you think about a typical transformer architecture, you have a number of layers. Llama 70B, I think, has 80 layers. And so you can basically take some number of layers, put them on one set of GPUs, some number of layers, put them on the next set of GPUs, and pipeline the activations through those. And then within each layer, you can do tensor parallelism. You take the matrix multiply you're doing, and you basically split that matrix up over a number of GPUs to get more parallelism. So by doing these things, we've gone over the years from training AlexNet on a pair of GPUs to a typical training cluster these days, maybe 100,000 GPUs running a single training job to train there's no way that I have talked for 15 minutes already. You need to start my timer when I started, not when I was supposed to have started. I understand how Berkeley Standard Time works here. Let me talk a little bit about software. So anybody can build a matrix multiplier. Back when I used to teach the introductory logic design course at Stanford, I think I could have assigned it to my class, and they produced a pretty good matrix multiplier within a week. But it takes a lot of software to make it useful. And in NVIDIA, we provide the software stack starting from the lowest layers, cuDNN, and then TensorRT that does the scheduling and packs layers of models together to avoid overheads. And then finally, verticals for things like self-driving cars and robotics and computer vision. But it's also critical to think that over time, the software actually improves the performance, because it's really critical that you get the software very, very fine-tuned and correct. And one good way of measuring performance here is to look at the MLPerf benchmark set. I think it's really it's an independent agency that publishes benchmarks and has pretty good rules about how to run them. And so people who make vast performance claims and don't have MLPerf results, I tend not to believe. But from one generation of MLPerf to the next, which is typically over a 6-month period, we'll see things like a 2.5x improvement in performance on the same hardware by improving the software. And this gives you an idea of how critical good software is for this. So let me, in whatever time I have remaining, which I think is more like 10 minutes, let me talk a little bit about future direction. So one thing we do to try to focus our efforts on where to put effort is to look at the best we can do today and ask, where is the energy going? And this is a pie chart, not from a GPU, but actually from an accelerator we build in NVIDIA research. And what you can see is most of the energy, that big blue area on the left side, goes to math. So basically we still have to make the math better, and that means better number representation, exploiting sparsity, not just on activations like we do today, but not just on weights as we do today, but on activations as well, and also more aggressive sparsity. And then the things on the other side have to do with memory and data movement, and there are a number of things we can do there as well. So let me present a couple snippets, and then I'll wrap up, since the timekeepers here are not letting me do Berkeley Standard Time. One big message is that whatever number representation you pick, you want to make sure you fit the set of data you have to represent with that representation correctly. And what most people do is shown on the left side here, where they take the biggest number they need to represent and the smallest number they need to represent, and they pick a scale factor that fits that range of numbers into their number system. And if you do this, you have very large quantization noise, and you have no clipping noise because you're not clipping. The other option you have is to say, well, these really big numbers and really small numbers are outliers. Let's forget about them. Let's pick a maximum and minimum that are much tighter. And if we do this, my quantization noise goes way down, but now I've introduced some clipping noise. And you can pose this as an optimization problem. I won't go into the math here. But if you look at the graphs, on the very far right side of these graphs is what most people do, where you represent the whole number line. So you have a lot of quantization noise, very little clipping noise. And as I move to the left, I basically am trading quantization noise for clipping noise to the point where they're both equal, and that's the minimum point on each of these curves. And if you look, say at the upper right graph here, the weight layer at 45, you're actually getting the same mean squared error that you would get with 4 bits that you would normally take 6 bits to get. So you're basically getting 2 bits of precision by doing optimal clipping. Another thing you can do is decide what set of numbers you're going to scale. And the way NVFP4 works, the way we're able to get performance out of 4-bit floating point, even for training, is by, instead of scaling a whole layer, which is what's conventionally done, we scale a vector of 16 elements. So with a smaller set of things to scale, we can basically scale it much more effectively and get much better performance. So let me talk about the interesting stuff before they drag me off the stage here. So if you look at LLM inference, there are really 2 very distinct phases. The first is a prefill phase, or context phase, where I take the entire prompt, not just the prompt you typed in, but that and the system prompt and any documents that were loaded by RAG. And there's an enormous amount of parallelism as I process all those tokens at once to produce the contents of the KV cache and the first output token, in this case, yes. But then I get into the decode phase, which is an autoregressive phase. Every token depends on the preceding token, and I've got to go through all 80 layers if it's Llama 70B, and more for some other models. And it's very latency sensitive, and it's also very bandwidth sensitive, because I have to read the entire model for each token. Every one of those 70 billion or 405 billion parameters has to be read. And these days, you don't just do that once, but before you give a token to the user, I go through a chain of thought, running that LLM multiple times, or even a tree of thought where I'll do things in parallel and then prune down what my final answer is. Let me skip over the agent here. And what this does is it really drives very different demands for the hardware you use for the decode phase, the prefill phase, which is very math limited, right? You have lots of parallelism. You can batch things up. You can crunch these tokens out. And it's not very sensitive to latency. And the decode phase, where because it's autoregressive, it's very bandwidth limited. I got to read the whole model every token, and very sensitive to latency. And so it drives very different demands, and you see deviation in the hardware generations for things that are optimized for prefill and optimized for decode. The other thing you have to be aware of is that models are constantly evolving. This is some figures from the DeepSeek paper. The Kimi stuff just came out. And people are coming up with really clever ways of optimizing the attention process, using mixture of experts, so you can have a trillion parameter model, but only touch maybe 20 billion parameters on each token that goes through. And by doing this, it means you need very programmable architectures. You don't want to hardwire your stuff, or somebody will come up with a model that you can't run. So let me wrap up here. I don't think I've used a full 20 minutes. We started late. They're trying to get on time by cutting my time short, and I don't like that. So anyway, to wrap up, deep learning was enabled by hardware. We had the air in the fuel, the algorithms and the data, and it wasn't until the GPUs came along and provided that spark to ignite that mixture and start our current AI revolution. Since then, we've been gaining progress in deep learning because it's taken ever more capable hardware to train these larger models on larger data sets, a growth of 10 to the 7th in demand over a 10-year period. The way we've done this is we've increased the performance of single GPUs by 1,000x in 10 years and by about 4,000x in 12 years. And this has mostly been through number representation and complex operations. Process technologies played a very small role. Software is absolutely critical to make these things usable and to realize the performance of that hardware. And I've given you some glimpses of things that we're doing to do more with less, including optimal clipping, vector scaling, and I had to skip over the sparsity. And so the current challenges I think we're facing is with disaggregated inference, figuring out how to handle the decode phase, which really stresses our current hardware in terms of latency and bandwidth. And then being able to handle chain of thought and tree of thought and agentic models that really drive up not just the amount of computation, but really also the demands on throughput. Because if for every token you give the user, I've got to run 10 tokens through a chain of thought, that means if I want to deliver 100 tokens per second to a user, I've got to have hardware that can do 1,000 tokens per second. And we have to do all of this in an environment where every day we see papers popping up on arXiv with clever models, new ways of doing attention, and things that really require that we be agile and have very programmable hardware. So thank you very much.
Going. I'm a principal engineer at Red Hat. I was previously an engineering lead at Neural Magic. We were acquired by Red Hat at the end of last year. We've been working on VLM for over a year and a half now, particularly on a lot of the performance engineering and inference optimization parts. So yeah, I wanted to give this talk on what is VLM, why is it important for LLM inference, what does it implement, and why is that important for agents? So first, it's important to state what is VLM's goal. It's a pretty simple and easy one: build the fastest and easiest to use open source LLM inference and serving engine. But first, before we think about that goal, we need to talk about what problem is VLM setting out to solve. So it's really, really important to say it's solving batch size greater than 1, and it's targeting data center hardware, the really expensive H200s, B200s of the world. This is unfortunately not the same workload as trying to run a 2-bit model on your laptop serving just yourself. Still use Ollama and llama.cvp for that. We love them. But when you're talking about this problem and this scale, we need to think about how do you efficiently schedule requests on each forward pass that you're going through the model as these requests are constantly coming in and out of scheduling, like think about serving a web server or a database at scale. We need to really think about scheduling efficiently. And then how do we manage the compute and memory requirements that come with LLM inference, like the very large KV caches we need to deal with long context workloads that agents love. So taking another step back and reminding what LLM inference is and why is this a hard problem. So if you forget about all the parameters and operations, an LLM is a function to predict the next token in a sequence. And to generate text or generate multimodal output, we need to chain together multiple forward passes through the model to generate each token in succession. So you see on the image on the right, sort of the yellow tokens are our input or our prefill that we process on the first step, and then the blue tokens that we're building up on each time step as we go down are our output or our decode tokens. And so a single request can take hundreds, thousands, tens of thousands of steps or forward passes through the model in order to generate all the tokens you need in your response. And so this obviously isn't efficient if you need thousands of requests for a single request. So how do we batch these requests together? So when you talk about batching, really kind of before LLMs, static batching was really popular. However, because of these autoregressive workloads can go on for very different amounts of lengths. You have some requests that finish in 10 tokens, some that finish in 100,000 tokens. If you batch all the requests together and keep that static, you end up with a lot of empty space and wasted work as you're going through these time steps here where we've already hit our end tokens and we're just haven't scheduled anything else. So obviously one of the most important things that were implemented was continuous batching. so that when a request finishes and we have our static batch, we can just insert in new requests that can pre-fill and run and start fitting inside the existing static batch. Second challenge is KV cache. So KV cache is the idea of if you keep around these two key vectors for each token, keys and value vectors, you can skip a lot of computation for all the previous tokens that you've seen in your context. And now the bulk of your computation is just on the new tokens that you need to process and are generating. This is obviously a great optimization, but it takes some memory cost. And maybe you only need 1 megabyte for each token that you have in KV cache. But when we're talking about 100K context, 1 million context, that turns into gigabytes. And then you talk about wanting to batch requests together, that turns into hundreds of gigabytes. And in large production scenarios, the KV cache ends up taking more space than the model parameters themselves. And so what VLM introduced in order to make this management easy is page attention, which is an attention algorithm that is based on virtual memory, kind of taking the idea from operating systems, that's where the V in VLM comes from, and introducing this block table, which gives us a layer of indirection so that the request thinks it has tokens in contiguous memory, but in actuality, these can be stored completely discontinuously in memory. As you can see here, we have 2 requests that are running. They have their own block tables. They think they have their own logical KV blocks. But in physical memory, these can be interspersed and reused even across requests. So that was the start and the genesis of VLM. You can see the paper on the left. And it's been a very rapid 2.5-year journey now of 50,000 GitHub stars, over 1,000 contributors, a ton of usage by the frontier model labs, by industry, by researchers, and it's really served as a great catalyst. And so I'm going to talk about why it has become that important catalyst. Of course, page attention fits in the optimizations there, but there's many other types of inference optimizations that have arisen since then, like chunk prefill, distributed inference, multi-layer batching. VLM has kept up in implementing a lot of these. But then, of course, there's the 100+ model architectures that VLM supports within this software infrastructure. And then, of course, the different hardware providers have taken the opportunity in order to use this software interface and build their hardware backends in order to harness and fit in this abstract software layer. So now I'm going to dive into a few optimizations with VLM and, what are we doing these days? So a really key one is automatic prefix caching. This is actually a really elegant optimization that comes from page attention naturally. If you do like multi-turn conversations or RAG where you're reusing shared context from requests, page attention just gives you this automatically because you already have the KV blocks in your memory, and for the next request, you just fill in its block table with the blocks that are already there in memory. So you can skip a lot of time in prefill, and this really helps improve both time to first token and your token throughput as you get higher and higher cache hit rates. This also works for multimodal data. It's a really powerful idea. Another key idea is quantization. You're probably familiar with this from other projects that mostly focus on weight-only quantization. We also focus a lot on activation quantization, so quantizing both the weights and the activations, allowing us to use those lower precision tensor cores and get more compute, more throughput out of the server that we're serving. And you can see we're sort of comparing unquantized versus 4-bit weight-only quantization versus 8-bit activation quantization. And as we scale the queries per second or users per second, we're able to serve a much lower latency and serve more users within our latency requirement with these types of quantization. And of course, KV cache quantization. We want to shrink the KV cache so we can do more batching and have efficient inference. Next, there's also speculative decoding. There's many methods to do this, but generally it's the idea of using some cheap way to generate many different candidate tokens and then passing those candidate tokens in parallel through your target model and then reading the output log probs to understand would the model have predicted these tokens anyway, and if they did, great, you predicted 3 tokens at once instead of 1 token at once. This really helps in the low batch size regime, pushing latency even lower and increasing your tokens per user per second, which is really critical for coding agents, for anything that you want to get a response faster, get tool calls faster, all those great things. And of course, with VLM, you're not choosing one of these optimizations. You're able to compound and stack these optimizations together as a system, offering compounding benefits. Now all those optimizations are talking about single node inference. VLM can of course go distributed, distributing your model across devices on a node and even onto multi-node cluster scale inference. So I don't have a lot of time, so I won't go over different types of parallelism, but we have tensor, pipeline, expert, data parallelism. These are all useful in different scenarios. And again, VLM can mix these types of parallelism together where you would like to do so in very different workloads. For instance, it's very different. You want to use tensor and pipeline parallelism when you're hosting a dense model like Llama 405B, but you would much rather use data parallel and expert parallelism when you're hosting a very fine-grained, sparse mixture of expert model like DeepSeek v3. And finally, there's the idea of disaggregated serving, where we can actually separate the prefill operation from the decode operation. This is a really important operation for like production usage, because this now means new requests coming in are not going to affect our latency or our sort of user metrics as we're decoding. Prefill is very, very compute-bound type of workload. Decode is much more memory-bound. Because we have less tokens we're processing, we're reading KV cache, where we don't have that great of a batch size. So that's all I wanted to cover really quickly. Only had 10 minutes, so sad. But hopefully you learned some, and happy to talk afterwards. Thanks to the over 1,300 contributors we now have in the project. It's a pretty insane metric. Yeah, check it out on GitHub. There's several other projects under the VLM project, LLM compressor, AI bricks, production stack, many other things. And please get involved. Check out the issues, check out the PRs. Let us know on GitHub if there's some feature you really want. Join the Slack and join office hours. We host these bi-weekly office hours that let you know what's coming, what's new in each release, and also have special topics with people from the community presenting on what they do in VLM. So. That's all. Thank you.
Jason Kim. I'm an engineer from Anthropic, and I'm here to speak about MCP. Thanks to Matt and RDI for hosting in this very crowded but nicely stained glass room. Anthropic has many UC Berkeley alumni or people who are associated, and so I won the battle royale internally to get to speak this time, but surely I won't be so lucky next time. In today's talk, we're here to talk about MCP as a foundational protocol for agents. And we hope this will tie into a lot of the other sessions that you're hearing throughout the day as well. Claude made most of these slides for me with MCP servers, so hopefully there are no surprises, but if there are, surely we'll discover them together. Before I really get started, I think it's kind of important in these talks to try and say the most important thing at the start and at the end, so that if you get a really good push notification in the middle, you still sort of got 90% of what's going on. I think the most important thing is sort of a request from Anthropic and from the MCP community. This is a newer open source standard, and we'd really like your participation. Read the docs, implement it yourself, PR against the spec, against the reference implementations, join the Discord, become a maintainer. These are all things that are helpful, we hope, to everyone, and so we'd really sort of request your feedback and whatever it takes to get involved. All right, so let's talk about MCP. Why are we doing this necessarily? The premise is that we believe, and I think most people agree, models are only as good as the context provided to them. Put another way, Anthropic is an AI safety research lab. The first public product we made was a powerful family of large language models called Claude. We have a number of tools that use Claude as well. But something we're finding lately is that if we have to make a trade-off on incremental benefit, it seems better to spend time giving models context rather than making the base model just a little bit smarter. Actually, I think this concept sort of applies to humans as well. Think about if you were going to hire me to work on your company or your project. It's probably better for you to just hire me now and give me a week of onboarding than to say, like, Jason, go study for a week and make your IQ like 2 points higher. This specific context is really important, and so we want to design MCP to make it easier to accomplish this task. This task is in service of this overarching agentic implementation that you've heard a lot about. It was mentioned in the keynote that just happened before this, before we all sort of like ran up the stairs and came here. As part of giving context to a large language model, What do we mean by this? We mean some of these purple boxes that are at the bottom. We want to give the models up-to-date data that it can retrieve in service of a request. We want to give it tools so that it can call and affect the environment around us. And we want to give it memory so that it doesn't make the same mistakes over and over again. If you've watched early versions of Claude Plays Pokemon, you know why memory is so important. We spend a lot of time sort of getting trapped in these trivial cases. And so how does MCP solve this? We've designed MCP to be an open protocol that standardizes the interface between AI-based applications and agents and the context that we're trying to give them individually. Again, context meaning tools, data sources, interfaces, possibly even other models or other agents themselves. We believe using MCP and adopting it more thoroughly can help us speed up this integration process. We're always working on security, which has been quite core to Anthropic's mission and has roots both in the open source and the enterprise community. And frankly, one of the most exciting benefits to MCP is to allow us to take advantage of the growing community around us. Every room today is so full, and the registration line was so long, and there's so many people online, and it would be a shame if we couldn't take advantage of the things that we're building if it's shareable, if we can implement them in each other's projects and pass those back and forth. The sharing thing is a little tricky because before MCP, we had a lot of parallel development. And I think this would happen within project teams, within companies, within customer groups. Everyone would go ahead and build their own implementation. So you'd see something in a session and you'd say, this sounds really cool. I've gone and built a project with Claude. I wrote some prompts. I did some API plumbing. I handled authentication. Maybe I wired up a little bit of a test set. And then if anyone wants to do this again, they sort of repeat this process in a vacuum, right? It's like we're never talking to each other except to share weird examples of things that went out of bounds. The advantage to MCP, we hope, is to allow for standardized AI development. There's two parties, so to speak, in the MCP ecosystem. MCP clients, which make requests and connect to these external sources of context, and MCP servers, which are the ones that nominate and provide this context themselves. We've already been doing a lot of this context providing manually. If you think about times you've hooked up a database or an API or a local file system tool to Claude, these are all examples of context that we provide on the MCP server side. And the hope is that we can make these things usable and reusable rather than having to rebuild this thing every time something changes in the space, every time a new model is made available. We know from past track record, these changes happen quite often. And so having this approach for standardization, we hope will make it easier for us to adopt. What can you do with MCP? I think there's a lot of examples, and I'm sort of interested to see yours. But one example we'll look at here briefly is providing this external context for things that models might know. We can assign Claude tickets in a software engineering context, which you might have seen if you've used Claude Code. And in this case, we can allow Claude to do things like look at our intercom tickets, look at underlying linear issues, reach out to the code base, author commits. These are all actions that Claude doesn't have built into it necessarily, but it's interacting with the world around it. And this type of MCP server approach is the way that we hope we can provide this sort of external context, taking advantage of what other people have built and specialized in. Linear or Intercom or GitHub or whoever, they might have already built an MCP server, and we want to borrow from that so that we can focus on what we want to build ourselves with an LLM. When I was building this, Claude was worried that we might not have internet in this room, so it gave me a screenshot of the same thing as well. We were prepared. So we won't do a full deep dive because of time. I think as I meant what I said up front is we do really want you to go read the spec, read the reference implementations, humbly give feedback to the community on ways this can be clarified. But I do want this to sort of get you thinking perhaps of how this might mesh with the other speakers and the other sessions you might hear today. We talked about this difference between MCP clients, which sort of invoke these context actions, and MCP servers, which expose these actions to us. These are all sort of areas that you might sort of have gone through in your own approach, and so these are options that you have in terms of borrowing from MCP-based components today. I think we've sort of talked about this before. There's room for people on both sides. Building a client allows you to connect to this network of approaches that other people might have already made available. And building a server allows you to sort of expose a best practice or an interface. If agents are going to use your tool or service or backend or front end, increasingly often, you might want to give them guidance on how to use it the same way you would give humans guidance as well. So we're authoring approaches for agents as well as for humans. We're always doing new things on MCP. This is the spec revision from last month. We're probably about due for a new one, so stay tuned for more details. You can read about this as well. And in fact, the place to read about this all that I keep referencing is here just for sort of specific reference. I think I'll sort of close this by going back to what I said at the start. Remember the most important thing. We really do want your engagement as much as possible in terms of joining the community, interacting with the reference implementation, giving feedback on the spec, joining the Discord. MCP is much bigger than Anthropic at this point in time. The success of it is going to sort of involve everyone in the community, but if there are things that Anthropic or myself can do somehow to make it easier or better for you to interact with the MCP spec, please do let me know or let us know. I think this is sort of the main goal we have in mind, and it'll be exciting to see what we can build and what the spec will look like in 2 or 3 months from now. So looking forward to it. Thank you.
Talk about natural language interaction protocol or universal application level protocol for the age of general AI. So let's welcome Ranji Sinha. Yeah.
Okay, good morning. Great to be here. So we have trained AI models using the entire internet to speak in fluent natural language. But when it comes to AI agents talking to each other, we are still stuck with rigid and brittle approaches because they are based on predefined schemas. So what if agents could communicate with each other just the way that we do using plain language? Just like HTTP unified the web, we are on the verge of a new standard for agents that is based on natural language itself. So the original work on the natural language interaction protocol, which I'll refer to as NLIP, it started in March of 2024. The ECMA technical committee was formed in December of 2024, and ECMA is the body that standardizes application level protocols. So I'm representing the ECMA technical committee and the NLIP collaborators in this session. So researchers from industry and academia are helping to design a universal and open protocol that is based on natural language. Now, today's systems use several application level protocols and APIs with rigid schemas, and it causes challenges in integration, interoperability, and version management. So the question is, could we apply the generative AI technologies to design a more smarter and adaptable protocol? So if you look on the bottom left, that's the traditional protocols, where you have agent 1 communicating with agent 2, and you have the message structures A and B. They all need to be the same, and as well as the one that is over the wire, that's P, right? Because predefined schemas, they all need to be the same. In contrast, the NLIP, agent 1 message structure doesn't have to be the same as the message structure for agent 2, that is B. And you can use generative AI technologies to translate between the structures. The only important thing is that the meaning itself should remain the same. So that's the essence, I would say, the essence of the idea. So NLIP provides a simple, open, standard, and common protocol for applications, agents, and services to communicate with each other and to us. It does assume generative AI capability at the endpoints. It follows a multi-turn request and response paradigm to ensure that the meaning is refined and well understood. And some of the obvious requirements for the protocol is got to be secure. It should enable various safeguards such as data privacy, data usage policies. It should be implementable across various underlying transports and API styles. It should support multimedia content, should be efficient, should be implemented in various languages, and should be standardized in an open forum. So NLIP uses generative AI for structure-independent communications. And as I just touched upon that in the first slide, all the 3 structures must be the same in a traditional protocol you see on the top right. And that forces a rigid API. There could be version upgrade issues. It limits extensibility. And there is tight coupling between the systems. NLIP allows structure independence. And you'd find that the structure for these messages are different or can be different. And use generative AI because it's really good at passing unstructured text to structured text. And it has really worked in practice. We have done quite a few POCs and reference use cases, and it's panning out pretty well. And of course, the more we do, the better we understand it, and we can update the specifications accordingly. So the scope for NLIP is currently it's communication between two AI agents within and across organizations, or between humans and AI agents. Anything that is legacy software or pre-AI or pre-Gen AI, that's out of scope. Now, there are several multiple single vendor protocols that have been proposed for various aspects of agent tasks, resource management, tool calls, and discovery. Some of the popular ones are the Anthropic MCP, IBM ACP, Google A2A, Cisco Agency, and several more. So NLIP can interoperate with them in two ways. Mode A, where NLIP can be the northbound API, and the single vendor protocol, the southbound API, and use the LLM to translate between them. And in mode B, the NLIP provides the interoperability across the different domains of single vendor protocols, and each domain can have multiple agents using different agent frameworks. And we have done some POCs that have panned out pretty well. But we believe that eventually, the industry should converge to an open standard protocol such as NLIP, or at the very least be influenced by it. Now, this is very similar to what happened in the early 1990s. All right? So every business app had its own protocol, custom client, bespoke integrations. You had several pre-HTTP protocols. But once HTTP was introduced and was widely adopted, and under a single general purpose interface like the web browser, it really simplified application delivery, interoperability, and unleashed the potential of the internet and commerce. Today, we have a fragmented ecosystem of AI agents, tools, APIs, and proprietary integrations. LLMs and AI agents don't all talk the same language. AI agents and chat are becoming a common interface for business solutions. So if you can define that single standard protocols, HTTP for intelligent agents, it can really unlock and unleash the scale and collaboration of agentic AI applications. This is the NLIP schema. As you can see, it's really simple and concise. This is it. And you can check this out at our NLIP project on the GitHub page. And I'll provide some links at the very last slide as well. So let's dig deeper into the message structure. I've highlighted the content field because that is really the key field. The rest are supporting metadata. So the basic structure of a NLIP exchange is a submessage. So the format stores what kind of content that you are sending. Is it text? Is it JSON? Is it image? Is it video? The subformat is a bit more of information on the format. So if it is text, what language it is. If it is image, what is that encoding that is being used. And the content is the actual message. So in this case, let's say, what is the weather in Berkeley tomorrow? Label is a simple name or tag, weather info, for instance. So NLIP message can consist of a sequence of submessages, but in most cases, a single submessage suffices. And I have a use case later on that talks about how we have used this submessage field as well. Right? It's really simple. Now, this message format is community-driven. So we are all the researchers are coming together to define this structure, and it aims to solve the Tower of Babel problem in agent communications. And you find all of these other protocols defining their own message structure. So the salient features is the primary mode of interaction is natural language. It could be typed text or spoken text, which you can convert using speech-to-text conversion, and we have a POC that has worked out really well. It supports vision, audio, and other modalities. Structured text is also supported, but that's not the primary means of communication. There is no need for custom configurations. Your configuration and policy exchange are all done via natural language. And you can use different AI models at the endpoints. We have experimented with OpenAI models, Gemini models, Claude, IBM's Granite models, and they've worked out pretty well. Now, NLP is not reinventing the wheel. It builds on tools and technologies that's already widely being used. So it runs on top of secure connections like TLS, runs on top of the authentication system, uses the base transit protocol like HTTP, and on your cell phone or computer, the NLP library can talk to the NLP server, which then talks to the business application servers for ordering, scheduling, or anything else. So the key message here is the NLP integrates seamlessly with existing system architectures and doesn't reinvent the wheel. So let's look at an example. So for the next few slides, I have a few examples that will make this a bit clearer. So Agent A is trying to introduce itself to register. And there is a version mismatch between these two endpoints. So Agent A sends a message, I am A running on URI-EU. Register interprets that and creates a structure. It has an idempotency field, and it didn't find that information in the message. So it marks it at X. And then tries to clarify with Agent A, are your operations idempotent? And Agent A responds back, I cannot interpret your message, which indicates that it doesn't support it, and Register smartly assumes and identifies that as idempotency is not supported, so it's false. And it may reconfirm that you are A with URI-EU and do not support idempotency, and it confirms back as that is correct, right? So this is a request and response to ensure that the meaning itself is refined and well understood. There's another example where it's a chat interaction, probably one of the most popular use cases. And this is, so the chat client inquires about the ECMA organization. So it uses the format text, subformat is English, and has the content, what is ECMA? The response from the chat server, again, format, subformat, and the content provides the response for the question. And of course, there are a few other fields which I've omitted. It's not as relevant. And you can find these examples in the link I provided. That's in the NLP project page. It's part of the specifications. This is a use case that walks through a federation amongst various agents. So the client sends the same question to the proxy server. The proxy server then sends this to the three agents, agent 1, 2, 3, that may respond back with three different definitions of ECMA. The proxy then combines the responses and then uses the submessage field and sends it to the integrator app to requesting that it integrate this, synthesize this, and provide one response, and which it does and responds back to the user. So this is an example how you can use the submessage field. In this use case, NLP has been shown to work with popular agentic AI frameworks like LangChain and Llama Index. And it also supports tool calling using standard protocols like MCP. So in this case, you have a weather chatbot where the coordinator agent that is based on the LangChain receives a user query and delegates tasks to a worker agent that is based on the Llama Index, which then accesses an external weather API using MCP or other protocols. The coordinator then aggregates the responses from this task and then returns a synthesized answer to the user. And it shows how NLP can work across agent frameworks and uses existing protocols. There's an example, a speech-to-text, where a customer communicates the intent using speech. We use an NVIDIA ASR model to convert the speech-to-text, forward that to the channel recommender agent using NLP over HTTP. The channel recommender finds the most relevant Reddit channel. This is a Reddit search, a Reddit channel, and then forwards that information to the search agent, which finds the most relevant or the most recent messages in each respective Reddit channel, and then stores that, caches that in the Redis database. And this is an example of speech-to-text, and that's also worked out pretty well. So key takeaways is that NLP is structure agnostic. It is not tied to any predefined schema. It allows flexibility across diverse data formats. It's natural language centric. You can consider this as an envelope protocol, and this will enable cross-protocol communication. And it's built for generative AI, and it supports use of LLMs to translate or mediate between different message formats. And it's simple, concise, open, and standardized. So the next steps and the status. Currently, NLIP is being defined and standardized under the ECMA TC56. The draft specification initial implementations are in our NLIP project GitHub, QR code on the top right. And we do welcome your comments and feedback. These are still very early days for protocols, so it will really help. And if you're interested in supporting in POCs, that's also very welcome. We are targeting a formal standardization in the second half of 2025. So if you'd like more information, wish to get involved, please visit this NLIP GitHub page and contact us using this email address. So with that, thank you very much. Okay, cool. On time? Excellent.
Okay, thanks for Ranjan's great talk. So let's go to next speaker, Dave Duta, right?
Thanks. Sorry for the delay. There was a problem with the slides. They have a PDF instead of my slide deck, but we'll try to keep it simple and safe, hopefully. So if you think about okay, as a show of hands, how many people are from academia? And industry? Mostly industry. So that's good. Because what I wanted to kind of talk about is, as you are looking at different architectures for building agents, so let's imagine that multi-agent is going to be the common design pattern for enterprise applications, maybe in a year or two. It's still not there, right? And a year or two is actually being very, very optimistic. So this is your new workload, a swarm of agents. Imagine a new enterprise with 100 agents running alongside, human workers. Basically, my swarm of digital minions, right? So now the question is, where will these agents run? Most people think today it runs in the cloud because that's where we are running all these agents today. There are these platforms, and these mega companies like OpenAI, Anthropic, Google, they're just running everything in the cloud. But that's today. But what we see in the enterprise is that it's going to run anywhere and everywhere, right from your shop floor to a battleship, submarine, all the way to your distribution center in case of retail. So the question is, how will you actually build these agents? How are you going to choose the models? How are you going to choose the systems and the entire stack? And now for an enterprise IT, this is a huge problem because now you've created multiple stacks, multiple systems that they have to manage, and the InfoSec, the security officer, is also challenged because you have to then define the security policies of everything. For people who work in the industry, you know how tightly controlled these systems often need to be because the data has governance rules, especially for certain workloads like in banks, healthcare. Data cannot often leave certain guarded walls. So we believe that one needs to have consistent technical architecture for running these agents. And so the question is, how do we design the next generation enterprise AI systems, not AI systems? Because AI systems in the research community, in the open source community, are sprouting like mushrooms, Cambrian explosion. Of course, there'll be consolidation. So in order to design systems, you go back to distributed systems, right? You go back to the basics of hardcore system theory, and think about CAP theorem, where you see that only two of the three properties of a distributed system can be true, between consistency, availability, and partition. Now the question is there something like this for a multi-agent system? Because why? Because a multi-agent system is also a distributed system. So that's the kind of question that we have started asking within our team in Nutanix AI. And then one of our engineers, I don't know if he's here, Janan, so one of our engineers came up with a conjecture. It was a claim that maybe there is a CAP theorem, indeed, for designing distributed agentic system, and we called it the bar theorem. And because it was it was a fun talk, we actually said, let's go and have, most of us go to a bar and decide on a napkin what we need to do. So we called it a bar theorem, which is essentially the three dimensions are budget. So how do I respond? How does an agent or an LLM, even an LLM, respond within a particular latency and with a particular compute budget? So that's your budget. And authenticity. So how do I know that the retrieval? So let's imagine a compound AI system, which the term was founded over here in Berkeley. A compound AI system is retrieving information. How do you know it's not hallucinating? What's the accuracy level? And then reasoning. So in reasoning, we are looking for human-like chains of thought that are logical. So now, if these are the three dimensions, we claim that any Gen AI system or multi-agentic system can prioritize at most two of the three aspects. And this, obviously, it's a very tall claim. So from within our team, a bunch of us got together to kind of, as computer scientists, when you want to prove a tall claim, you start with smaller claims. And so we have some initial results that we are soon going to be in ArchiveX, where we've actually shown that for certain scenarios, this is actually true, using formal mechanisms. So, but over here, let's look at the bar theorem in real life, right? So if you think about enterprise AI, most of the common use cases, 90% plus use cases, basically talk to my data. Talk to my data, talk to my code, talk to my data warehouse, talk to my time series. And that's basically, you want cheap retrieval, you want less hallucination, because you don't want data retrieval or a query system or a RAG tool give you false results. Then you want to take an action, you want auditable trails, and you want some kind of reasoning, mild reasoning with some small LLMs, and you want it to be cheap too, right? So there are these RPA agents and a bunch of other agents where you can build pretty much with open source small models today. But they may not be very highly accurate for retrieval. But then there are these large compound AI systems that we all know about, deep research agents, coding assistants, and very complex video generation, which is pretty good. But the price that we pay today, somebody's subsidizing it today. When we all have to pay for the ChatGPT and the Anthropics of the world, and there has to be a P&L budget associated, I think the cost will be much more than it is today. Unless this community can design very, very cost-effective solutions to bring down the cost by 2 orders of magnitude, it's going to be hard. So our claim is that this bar theorem is going to be true in real life for a while. Now, if you think about an enterprise, look at a bank, a hospital. We all have to go to a hospital. We have to go to a retail store. When you want to design agents that run all the way from a retail store to a packing distribution center to the headquarters, data centers, and in the cloud, if you look at every data scientist today, they all want 4 to 5 LLMs to build an agent. It's not just one LLM, right? You need an embedding endpoint, you need an inference endpoint, you need re-rankers and guardrails and so on and so forth. So if you look at an entire cost to the enterprise, the TCO is astronomical. And most of these data scientists today, including in my own team, a bunch of them are here, everybody loves to run VLLM, again from Berkeley, or pick your favorite inference endpoint in a container and just run it and not have to deal with any other thing. Like I just run it on my laptop or running it on Olama. So that is what's happening today. But what the IT departments of enterprise is petrified and paranoid, because it just leads to a huge problem with security. It's complex to manage, the security risks, it's just expensive. So our strategy for at least, with the budget part of it and complexity part of it, is to kind of shrink everything down into shared enterprise grade endpoint management and consistent architectures, starting with Kubernetes. Internally inside the company, we've standardized on vector databases using open source. Basically, everything is open source, using Postgres, PG Vector. So we have an entire stack that we use to run multiple agents, and the agents can come from with any kind of tool chain, and you can have any kind of communication protocol. That's for us. The technical community will figure it out. For me, the first thing is, how do I manage the costs? How do I make it easy to deploy? I partner with my CIO to make sure that we can do this inside the company in a simple, secure, and efficient manner. I'll end the talk with a couple of non-technical stuff, which is very important as you design systems. There are three dimensions of AI, at least in Nutanix and in most enterprise companies that I talk to, are people, tech, and process. Of course, this conference and most conferences and the entire valley is focused on the tech, which is the right thing to do. But when we look at deploying these agents in actually enterprise companies, banks, hospitals, companies like Nutanix, retail stores, people become a huge issue of dimension, in the sense that we need to upskill existing employees to learn AI, to understand how to even deploy, even operate these agents. Because at the end of the day, autonomous agents are still going to be a thing in the future, right? Thing of the future. It's not happening anytime soon. So, and the other thing is processes. Today's enterprise already have fixed processes. We all love to, in this conference, want to talk about multi-agent systems, talking to each other using some protocol, but that's not how they will be deployed today. There has to be a change in processes. How do you show the ROI? Think in terms of, if you spend $1 million building and deploying agents, are you going to get $5 million worth of ROI? That's still an open question. And the other thing is that coming to an enterprise is not just engineering, right? A lot of people are very concerned. So you have the AI team that wants to do the cool things, the right tech, and then supposedly they are being slowed down, but it's not slowed down, because in a regulated industry, the IT comes in and says, you cannot run this wherever you want. You can't just run a VLLM container where you want. And then there's a legal team that says, how are you going to run this brand new model just popped up in a leaderboard, because I don't even know whether you can even use this. We don't know what the data provenance of that model is. So there are, again, three dimensions in an organization, and these three teams. So I'm usually in meetings with these three stakeholders, IT, the legal team, and the AI team, to figure out how do we change the processes that I talked about in this. And for each of this, is there a theorem that we can prove, or a conjecture that we can come up with? How do we keep everyone happy? How do we show ROI in the enterprise while doing the right technology over here? Because we are all technical folks here. So anyway, the key takeaways is that multi-agent systems are going to happen. They're going to happen slowly, as you can see. 4 to 5 LLMs per agent, 100 agents. Think about this, and LLMs are becoming small. They're getting better at reasoning, but you need to run these agents close to where you want to do your business. maybe in the bank, maybe in case of military, somewhere else, right? In the field, battlefield. And you need to run agents and then you need to design these agents. They are distributed systems, so think about what are the real technical barriers, where is the sweet spot for designing these agents, and manage your infrastructure sprawl. Don't think of that, even as technical folks. Think about when you're building something, how is this going to be managed, deployed, used? So I think with that, prioritize not just tech, but people and processes when you're thinking in terms of computer science. But I feel CS is a wide enough field. It's liberal arts today. You can actually apply computer science to all the 3 dimensions. And with that.
Good morning, everyone. Thanks for joining us at this Agentic AI Summit. This is the frontier stage, so I'm going to present a very new project, new open source project that's pushing the boundaries of the collaborative AI. How new is this project? It's just 7 days old. The first MVP was just out 1 week ago. So good luck with me. I've never presented a project as young as this one. In one word, this is a multi-agent scaling system that runs multiple agents, diverse agents, in parallel, sharing intelligence and refining each other's work. Okay, and you can check the GitHub from mathgen.ai link. And yeah, let's dive in. So if you have followed the recent breakthroughs from Grok Heavy or Gemini DeepThink, it's easy to see the inspiration. Harnessing multiple AI minds that tackle complexity far beyond any single model can do. Okay, there's a lot of recent exciting things about it, and the North Star is that we want to build co-evolving agents through collaborative interaction. So many of you have probably know that I've created this AutoGen open source framework since 2023. I've been working on IDEA and now AG2 for these multi-agent conversations. But many challenges still remain, and especially with the change of the new technology. In April this year, I wrote a blog post called Myth of Reasoning, and I talk about this thread of thoughts idea. And the key insight is that the human reasoning is actually much messier than what most people realize. So most of the time we have intuitive thoughts, and only after that we try to find justifications or find it's wrong and restart this process again. And but we need to make it cleaner for presentation, for communication, to convince others. So the nice chain of thought is not a start. It's the outcome of this messier processes, and by nature it's collaborative, right? So that's kind of one of the key insights I've been working on in the past few months, and recently I've seen real evidence in practice. So Grok Heavy and DeepThink, they prove that this is not just theoretical, it's practical and deployable, right? Let's take the Grok Heavy as an example. If you check their performance on last human exam, right, very, very challenging benchmark. Grok 4 standard achieves about 38%, and Grok Heavy achieves about 15% higher. By doing what? The same model. They're using the same model, but just using multi-agent architecture. And they price it 10 times higher, right? $30 versus $300 per month. So that's basically the price just for this multi-agent architecture, nothing else. And by the way, DeepThink, Gemini DeepThink is also available now in Google Ultra, also in the highest tier subscription. So I think these are like the most strongest commercial evidence I've seen so far about the power of multi-agent architecture. But what if you don't have access to those expensive subscriptions? I have the good news for you, okay? Just if you use MathGen, you can just use any existing API keys you have to any models. You can easily kind of run this experiment of multi-agent scaling, right? You can use a single model with different configurations or mix multiple different models or agents, right, as you want. And how this works is this messaging orchestrator will take a user's query, distribute that task to the multiple agents, and run them in parallel. And the magic happens when there's this shared collaboration hub, right? So all the agents, they can check the real-time updates from others, criticize and refine the results, right? And if some agent finish the work, but other agents have new updates, then the agent might get restarted. And eventually they will converge to some consensus and generate the final answer. So that helps refine the quality. And here we can see that the multiple ideas are integrated together. We want to kind of leverage the strengths, unique strengths for different models of different providers and different agents. And we want to run them in parallel to slash the latency. But in the same time, we want the agents to be able to absorb and take intelligence shared from others and improve their own work. Okay? And this iterative refinement keeps going until the consensus. It's very easy to get started. You can simply clone this repo and install some minimal dependencies and get your API keys configured. Okay? And then you can use the CLI to run some configurations. You can configure them differently and try them out. You can either use interactive mode to have multiple turns, conversations, or just ask simple questions. Let's do a quick demo here. So I already have VS Code open and already cloned the repo. So I'm going to try to run the latest version. If you are using the main branch, you may get a slightly different result. Here I'm using a 3-agent default configuration and asking, give me all the talks on agent frameworks in Berkeley Agent AI Summit 2025. Okay, let's run that. Okay, here the system gets started. You can see the question on top and the 3 agents running in parallel. The first agent using GPT-4o, second one using 4o mini, and third one using Grok 3 mini. And you can see all the agents are working in parallel. Some of the agents have access to building web search tools or code execution tools, so they will invoke them when they need to. We can see that some agents already finished work, like the 4o mini already provided some answer and have several rounds of voting already. And okay, after the working, we finally selected one agent called the 4o agent. Let's see, and the 4o agent is doing the final presentation to generate final answer. Right? You can see the whole process, and the 4o got 3 votes here by the end of the interactions. We can check the output for each agent. Here I enter 1, so let's check agent 1's working process. So this is a log, right? We see that it started with some web search. After search, it generated the initial answer, like this. It found a few talks, some final discussions, and gave a link to the Berkeley website. And later, it has some voting about the agents. Okay. And you can also check the second agent, the 4o mini. Yeah, it generates some answers as it didn't use web search, so it didn't find the right information. Let's see the Grok 4 mini. Yeah, the initial answer from Grok 4 mini is they don't have access to the information, but later once it sees other agents' answers, it updated the answer. Actually, you can see another answer provided from here, so it actually updates the answer. But eventually, it's also voted for all. Okay, and the final answer is presented by 4o, and it combines the information from all the different agents. Okay, so that's a simple demo. You can try this out and try different queries. There are a few earlier case studies when we had the first version. So this was using the current main branch. And we tried a number of different examples. For example, we ask agents to find who is IMO 2025 winner, which AI wants IMO 2025. And we can also ask open-ended questions like do some collaborative writing, write a story for like robot music stories. And we can also ask very hard questions like how much does it cost to evaluate Graph 4 on the HRE benchmark? This is an open question. You can't find any information online to directly answer these questions. But some agents can find a piece of information from the website, and some other agents can use their code execution, data analysis capability to do the estimate. So eventually, the multiple agents can collaborate to try to answer this question. We can also ask questions like travel guide, like if I want to travel to Stockholm in October, can provide a travel guide? Usually, a single agent will find some information, but each of them will find slightly different information, and only when you put them together, you get the best answer. So from this case study, you can see there are several different flavors or reasons why this multi-agent scaling can help. For open-ended questions, usually different agents will have different perspectives, and you really get the best answer from combining them. And for many other hard tasks, it requires many different steps. Usually, the initial answer generated by any single agent is preliminary, but after they see others' work, they get inspired and they keep refining their work, and you usually get better answers. You can also understand this from another practical point of view. I don't know how many of you like using multiple AIs at the same time. And when you have a hard question, you try one AI, but you don't really trust the result. So probably you will try another AI and cross-check to make sure you're not fooled, right? So this kind of simulate that automatically, right, by having the multiple agents cross-checking each other's work. But it goes beyond that because it doesn't stop at the first round. It actually try to push them harder, right, to make them further work more, and until they get the final comprehensive answer. So yeah, you can find some of the case studies from the website as well, from the GitHub repo. There's still a lot of, this is very new, right? It's just a start of this direction, and there are a lot of whole set of challenges ahead. The eventual vision we want to have is to have this recursive scaling, so that every time you get a new agent, you add to the system and it amplifies the whole. But we are far from that. So there's a lot of challenges like consensus, shared context, and interoperability, right? We have heard many great talks about addressing these issues. Eventually, we need to solve all these hard problems. But if this really works, then we can have AI that's kind of similar to how we scale ourselves, right? AI can scale themselves too. Yeah, so that's a very brief introduction about this project. This is just the beginning. I hope you can check the repo on GitHub, start it, start discussion, join our Discord channels, and build this together. By the way, the new version I just used is coming soon, probably this weekend. Yeah, so I will get the chance to try it out and share your feedback. Yeah, thank you very much. I think I still have time for questions.
So any question for Chiwan's talk? Okay.
It can be customized for me running several coding agents, orchestrating other type of tasks.
Yeah. Great question. Yeah, coding agent is one most important kind of capability I want to integrate into this machine. Why is coding a big deal? Because it's a meta power, right? An agent that can change its own software, can self-improve, can experiment, can learn and spawn even new sub-agents. And yeah, you have seen the strong, powerful coding assistant like Cloud Code, Gemini Cli integrated into our developer workflows. And yeah, so but right now they are working alone, right? So the single agent working alone. And if we can integrate that into this multi-agent parallel working paradigm, I think the power will be amplified to a large degree. So that's the big next milestone I want to achieve. Great question.
I have a question about like if we have, for example, multiple agent booking a ticket,
Yeah.
so they try to book it all together. How can we ensure that they don't overbook and double book, or how can we check that each of our tasks whether it's failed or not in a kind of holistic way?
Yeah. This is like it touches very important about like conflicts, or sometimes the agents' work are not easily kind of scalable, right? That's exactly the kind of the challenges we need to solve, especially when now each agent can go beyond question answering. They also have built-in tools that often can do things. So right now we're not giving the agents that kind of tools. We're only giving them like search, code execution, and they can work in isolation. But as soon as we get to the point where the multi-agent might be working at the same workspace and they have conflict, we have to find a way to resolve that. So that's kind of a great research question to look at next. Yeah. Thank you.
Thank you.
So I have a great
thank you.
talk. So I have one question. So in context learning, we have, let's say, some poor quality examples. It might hinder the whole trajectory. So I want to see, let's say, if you have multiple agents and we are scaling up,
Yeah.
and some of the runs are lower quality. So what is your vision? How we can make sure that doesn't like hinder the whole trajectory for the agent?
Yeah, exactly. So actually the demo just shows that exactly, right? So 2 agents actually provide very poor answers in the beginning. Only 1 agent find the right answer. And I think this requires some fundamental capabilities to the base models and agents. So each agent has to have a basic way, evaluation capability. So giving multiple answers, it needs to know the relatively better answer for the most of the time. Otherwise, it will not work. I think this built on the assumption that the model has been improving to a point that most of the strongest frontier models have that capabilities. But this is a big assumption that we do need to check. I actually wrote this down in my blog post. I think there are several basic capabilities we need to have. This is one of them. Yeah.
Good morning, everyone. I'm Jay. I'm a developer advocate at NVIDIA, where I focus on building LLM application. And today I'm really excited to talk to you about how to build agentic workflows by harnessing the power of NVIDIA GPUs. So let's start with a quick timeline. We have had single call LLMs for a while now, where you send one prompt and get completion back. In 2024, it was RAG, where you basically do vector stored lookups to pull in up-to-date information. And this year, it's the year of agents, where you stitch multiple LLM calls, tool invocations, and reasoning loops into fully autonomous processes. But the true power of this new paradigm is realized when agents work together. Think of an enterprise ecosystem where there are multiple departments which have their own agents. So in this, but to build these kind of multi-agent system, like for enterprise level, like it's really difficult building this kind of workflows. You might face many challenges, which could be architectural complexity, making different tools from different frameworks work together, and there's also problem with the performance and the reliability. And to solve this problem and to manage these systems, earlier this year, we open sourced a framework or toolkit called as Nemo Agent Toolkit, and it is designed to be the glue for your existing agent workflow. And it does that by using universal descriptors. So what it does is it basically converts every tool, agent, or memory into a function call. And you can piece this function call together, whether it's LangChain, Llama Index, or something that you have built yourself. So let's take a quick demo about how to build these GPU-accelerated multi-agentic frameworks. So in this case, imagine there's an enterprise with multiple teams, and those multiple teams have their own agentic workflows built with different frameworks. So in this case, there are 3 agents: HR, finance, and IT. And these are built with different agentic frameworks with their specific or relevant knowledge bases for their specific departments. So we are combining these all 3 agents and controlling them using a supervisor agent, which is built with LangGraph in this case. And this all pipeline is built using Nemo Agent Toolkit, which is open source. And this all pipeline is monitored using Phoenix, Arise Phoenix, which is an open source observability tool. And the RAG tool in this case is completely GPU accelerated. Vector database is being run on Milvus, which is open source and supported by NVIDIA. Then there's LLM and embedding models are also running on GPUs. Specifically on NIM, so it's basically a containerized solution to deploy open source LLMs and embedding models with just a single command. And in order to piece those workflow, you have to simply configure a YAML file where you basically mention all the tools that you have access to. And this is too verbose, but what I'm trying to run here is basically running the entire pipeline by giving it a prompt about, hey, what's the parental leave policy? And once the workflow runs, the supervisor agent recognizes this is an HR query and redirects it to the HR agent, giving you the final response. And on the right, it is Phoenix, which is basically tracing the every step of the interaction with this agentic workflow. So this is it. So the future of complex AI isn't just a single agent, but it's multi-agent working together. And Nemo Agent Toolkit helps you achieve that. And the GPU acceleration is what makes this all real time. So if you'd like to learn more about what tools we offer and want to stay up to date, feel free to scan this QR code and join the developer program. That's it.
Hello, everyone. Good morning. Excited to be here. Great talk so far. So I am a senior scientist in Amazon working on building multi-agent framework for automating SOPs. So it's complex industrial SOPs, which is beyond simple tasks. Is it better now? Yeah. So, the SOPs are something that human associates follow. They're written by humans for humans, not really meant for machines to comprehend. That's where the additional challenge comes in when we are trying to automate them using multi-agent systems. So they are much more ambiguous, open to interpretation. There is a lot of reasoning going on, diverse tool calling, and then also interaction of multiple agents. So I'll give you an example. So in the shipping industry, it's classifying a product, whether it's dangerous or how hazardous it is. It's a very common problem. So so they have to, so associates who make this determination, and not everything can be actually done by ML models. So you need human associates looking at different like safety data sheets or other multiple different data sources and actually making a decision and then classifying it. So how would an agent accomplish something similar, right? So it seems simple for humans. Humans have been doing it for a while, but when you try to have like an agent or multiple agents follow that same set of instructions, there are many nuanced reasoning, and like you have to call the tool multiple tools with precise parameters and interpret the values. Sometimes some APIs may fail. You still have to orchestrate the whole workflow, right? So that's like from an agent perspective. What about the developer? Like there are many decisions the developer has to make, right? So we need to know whether it's just a simple function calling agent or is it going to be a multi-agent framework, reasoning between steps, how much of it should be in the context, how much of the background knowledge of that org or of that of the documents should be put in a knowledge base. And then the reliability. A lot of the speakers before me have mentioned the costs as a big factor. Then how do you make these decisions? That what's more important for that use case? Accuracy, reliability, cost, latency, etc. So there are lots of decisions that a developer needs to make. So where do you make those decisions before you actually deploy your multi-agent system to automate complex industry tasks, right? So we couldn't find benchmarks that were readily available. So the ones that are currently very popular are like Gorilla benchmarks, GAIA examples. seem, I mean, there are lots of results on these, and LLMs seem to be doing well on these, but the same agent framework in these examples didn't really help with comprehending and automating complex SOPs. So we ended up building a benchmark of our own. So we have this is available on archive. We'll be posting on GitHub soon. It's a benchmark of like 10 different industry use cases, like starting from customer support, aviation, retail, even healthcare. So we've created SOPs, like long instructions, along with the tool APIs and the code, like a mock. Like the code is obviously a mock of the real APIs, and also data sets. And at every stage, we have had human intervention, like human validation, like a scientist validating the code, the industry experts validating the SOP and the APIs, and the data sets. So it's like, so for a dangerous good use case, you actually have the data set, which has the input and output of every API call, what you expect. So you have the safety data sheet, the handling and storage restrictions, etc. So it turns out like building the SOPs was not straightforward at all. It was like a very hierarchical and complex way of prompting and creating these different aspects like SOP as well as APIs and data sets. So an evaluation is like much beyond pass and fail. So here, like I'll give an example. So we want to make sure that it goes through the whole execution workflow. So we tried only two paradigms so far, like React and function calling. And as you can see, on an average, it gets 35%, like 70%. 70% actually like successfully executes, and only 35% of them actually have correct answer. So it's like we have a long way to go before we can actually reach the 95, 97% of human level accuracy. So it turns out synthetic data is powerful. So we want to try out these different agentic applications and improvements before we actually go and test out on real production data sets. And so the key thing is that before automating something with multi-agent systems, there are lots of decisions we need to make, and we need to build realistic benchmarks where we can we can feel confident on those before moving to like shadow and production. So we invite people to we also have the benchmark generation code available, so people can build benchmarks, add to SOP bench, so the community can actually keep growing. That's it. Thank you.
Right. So we're talking about Auth for Gen AI. So Auth0 is an authentication and authorization platform. You can plug Auth0 to provide authentication authorization services into your apps using our APIs or SDKs. We've been around for 12 plus years, and we primarily target developers with this. So as we started seeing a rise of generative AI applications and developers trying to build agentic apps, we recognized that there were some very strong use cases here where agentic apps weren't securely trying to access APIs or data sources. So let's talk a little bit about that. We introduced Auth for Gen AI. It's available at auth0.com/AI. We're going to talk about why. We're going to do a demo, quick starts, talk about some resources. So just to kind of set up the stage here, what we have in a typical generative AI application or an agentic app, there's a user prompt aspect that a user asks questions from. There's some sort of an output that is generated. There's LLM inference that's used. There's some sort of agentic planning and orchestration that happens, typically provided by a bunch of these different frameworks today. And then many of these times, there are some tool calls that are made to third-party APIs or services. These can be over REST using newer upcoming protocols like MCP or Google's agent-to-agent. And this is so that an agentic app can securely access data sources to add more context to the responses that it provides. So this happens over tool calls. And then finally, there is also an aspect where agentic apps that are sometimes running in the background, they have to reach out to a user for some sort of an approval process. They might be processing some kind of a purchase or some kind of a transaction or something, in which case they reach out to a human so that the human can authenticate and authorize that transaction. And so we call this an approval process, and a human in the loop is required there. So this is a general setup of how we look at this space. Now, there are 4 authentication and authorization requirements when it comes to this scenario. First, the AI agent needs to know who I am. And this is a standard authentication. Someone needs to be able to there needs to be a way for users to log into their chat app or chatbot or other agentic app, so that the agent actually knows who's logged in and what they're trying to do. The second requirement is around the need to call APIs on the user's behalf. And so this is where, if an agentic app, let's say there's a sales agent, or let's simplify it, maybe a fitness coach agent that someone is trying to build. Now, that fitness coach agentic app is going to need to access perhaps a user's fitness apps or data from Google Fit or Strava or some other app. And so providing this agentic app an easier way, a secure way to connect to a user's services and APIs and get data from it is another one of these requirements. Then asynchronous interactions. This is where an agentic app that might be running in the background, and now it needs some kind of a human approval process, needs to reach out to a human and get that approval is another one of these requirements. And then finally, via RAG, retrieval-augmented generation, a lot of agentic apps can access data, but there needs to be some sort of way for them to only access data that a user's permitted to access. So as an example, you might ingest a lot of internal company data into RAG, into a vector database, so that you can have an agent provide answers based on those files. But it might be the case that I, as an employee, shouldn't have access to certain files or certain types of data sources. And so there needs to be some sort of an authorization layer in the middle that prevents that RAG-based access to get all the files back and filter out the ones that I'm not authorized to use. So these are the 4 use cases. AI needs to know who I am, call APIs on the user's behalf, use asynchronous interactions for human in the loop authorization, and then also have authorization models so that it can only have access to data that I'm as a user I'm authorized to use. So with that, for these, to tackle these 4 requirements, we built Auth for Gen AI. I'm going to give you an example. We're going to focus a little bit on calling APIs on users' behalf. So I'm going to give you an example, a demo of what that looks like. But before I do that, we have everything available at auth0.com/AI. Talks about the 4 use cases. There are docs that talk about all of the different use cases, quick starts on how to get going with authentication, calling APIs on users' behalf. There are a lot of how-tos, as an example, how to check, how to have an agent, how to provide an AI agent the ability to check a user's Google Calendar or list a user's GitHub repos, get Salesforce opportunities. And the other thing I want to call out here is the examples are both for JavaScript and Python frameworks, and we have a lot of different frameworks that we support. Vercel's AI SDK, LangChain, LangGraph, Google Firebase, GenKit, Llama Index, and more. So there's a lot of how-tos there, sample apps, SDKs are listed here in guides. But let me get to an actual example. This is something that I just recently built. It's a playground. It's running on my local host here. And the first thing I do is I log in. So this is authentication. I've integrated Auth0 to log in into the app. And I'm just going to go continue with Google. And I end up in this chat interface where I can ask questions. It's just backed by OpenAI to provide answers. So this is a Vercel AI SDK-based chatbot app that I've created. Now on the left side, you can see that I have a lot of connected apps that are either connected. Some of them are connected, some of them are not. And what I've done here is I've linked using Auth0 these third-party apps to this agentic app that we're in right now, Playground Zero. So what I can do as an example is I can ask questions like, get 3 opportunities from Salesforce. And what it'll do is it'll leverage the token that Auth0 has managed on behalf of the user, on behalf of me. This app will get an access token from Auth0 to call Salesforce APIs and answer the questions that I'm asking it, right? So to kind of give you another example, what I'm gonna do is I'm gonna show you how to connect HubSpot to this. So I click on HubSpot. By the way, the source code for this is on GitHub, and you can take a look at that, and we'll also take you through a little example as well. So I click on link account. And what it does is Auth0 redirects me to an application that I've set up in HubSpot's developer portal. So I select that. I say connect app. And it fails for some reason. Okay, let me do this. Sorry, 1 second. This is what happens when you run a live demo. Log out. Try to log back in. It connected, but let me see. List HubSpot contacts. Okay, so there's probably something messed up here, but the account linking worked. It didn't revert back. Maybe the callback URL is not correctly configured. So it connected. What it did was it redirected me to HubSpot so that I could log in using my HubSpot credentials. And then it should have redirected back to the app. But when it does, you can see that it linked HubSpot, my HubSpot account, to this agentic app. And now I can ask it questions. List HubSpot deals as an example. And what this is doing is, again, I'll show you real quick. It's basically doing a tool call to HubSpot in this case, using the access tokens that as part of that account linking that we Auth0 negotiated for that. So let me go into to kind of show you how this is set up. So the first thing we do is we have this is Auth0. This is a tenant in Auth0, and what we call is social connections. We configure social connections, and these connections enable Auth0 to negotiate tokens on behalf of the application developer. So in this case, I have a HubSpot connection set up. I have a Google, GitHub, and what a connection typically entails is linking up the authorization URL, which you can typically get from HubSpot's developer documentation, the token URL, what scopes we want the token to access, and then a client ID and a client secret. So these are the things that you need, and enabling something called Token Vault, which enables Auth0 to then negotiate a access token and a refresh token on behalf of the user and store it in Auth0 and do the token refreshes on behalf of the user. So once you have this these connections set up, I'm going to show you what the app here looks like. So this is the playground app. And this is a versatile AI SDK-based agent. This right here is the chat route, where I have some sort of a system prompt, the model that I'm using, and then the tools that I'm calling here. And the tool calls are where all the magic happens here. But before I do that, I'll show you what the tool looks like. There's also configuration of a .env file where I have to add all of my auth0, the domain, the client ID, client secrets, etc., so that I can configure that. I also have to integrate auth0 by configuring auth0 client. And then one of these tools here is the HubSpot tools. And so what you can see here is a tool called List HubSpot Contacts. And it basically gets a list of contacts from HubSpot. And the key part here to notice is this right here, which is where to enable the tool to make a call to the HubSpot API. I'm getting a token, an access token from auth0. And this SDK command here, auth0.get access token for connection. The connection type is HubSpot custom. Basically enables this tool to call auth0 to get an access token for HubSpot on behalf of the user so that it can call the HubSpot APIs and get the contact details or the HubSpot deals or anything else that you have built in the tools. And these connections are basically what we configure in auth0, so that the app can ask for credentials on behalf of the user. So in a nutshell, this is the setup, and to be able to build agentic apps that allow securely calling third-party APIs on behalf of a user. So I'm going to pause here. We have all of the samples and examples are available on GitHub. A lot of the examples there are also other sample apps that we have under here, under the sample apps section. We also have framework-specific SDKs. So if you are if you have a standard Next.js or Fast API or Fastify, then you can use what I just described. But if you also want to natively integrate with LangChain, an agentic app that's built in LangChain or Llama Index or GenKit, then you can leverage our AI-specific SDKs. And so what I'm going to do, I'm going to pause here. I'm going to pass it over to Christian, who's going to demonstrate how to configure something using our AI SDKs. Christian?
All right, awesome, thank you. So as we're seeing, we have specialized auxiliary AI SDKs. As we mentioned before, we're trying to solve it for developers is the problems around building agentic apps for authenticating users, calling APIs on users' behalf, solving authorization for RAG, and async user confirmation, all the examples that Karen just showed us. So the AI SDK basically provides you with different tools to solve these problems. And in addition, we are also creating like specific integrations with different frameworks that are out there. As you know, all the different frameworks for AI have subtle differences into how to solve specific like tool definitions or calling RAG or stuff like that. So we are trying to unify that experience around Alpha-Ocean AI with this SDK. What we're going to showcase right now is basically the same example or similar example that Karen just showed us, but this time only around Google. And well, hang on a second. I forgot to mention something before mentioning that, is that we not only have an AI.js SDK, but we're also building an AI Python one. So if you can build it, solving the same problems, having a very similar interface integration, and for Llama Index and LangChain, for example. So what I'm going to show you right now is, again, a Next.js application integrated using AI SDK. In this case, you can see how here we are passing down the tools, and we have a check users calendar tool using the Next.js Auth0 right now to get the access token for this connection, right? So this is, again, a very similar chatbot application where a tool needs to call a third-party API, in this case Google, on behalf of a user, and we are trying to get the access token here. So I have prepared a few copy-paste snippets, and I'm going to walk you through. But essentially, what we're going to be using now is the Auth0 AI Vercel SDK. So we're going to start by installing this SDK. I'm going to go a little bit fast, and maybe so that we have some time at the end for questions. So we are starting the AI SDK, and the first thing that we're going to do is initialize this SDK by, hang on a second, creating a file here, Auth0 AI, and pasting the initialization. In this case, you can see that we are importing Auth0 AI. We're also importing the Next.js Auth0 that we have just initialized. Why? Well, we are trying to build something to wrap our tool and ask for the specific scopes under a determined connection. So this is what Auth0 AI SDK does, right? So you can build a number of tools. You can have different tools called in Google with different scopes and have different ways to protect that tool, or to authorize that tool, or request tokens for that tool. And in this case, what we are doing here is we are providing the tool with a mechanism to obtain the refresh token of the currently logged in user. The reason we are doing this is so that you can use Next.js Auth0, you can use Express OpenID Connect, you can use any other framework that provides authentication with Auth0 ideally. In Python, for example, it's Authflip. And it doesn't matter the tool you're using, we're unifying the experience here. You just need to provide a way to retrieve the refresh token for Auth0 AI SDK to make this exchange using the token vault feature that we are released. So I'm going to save this file. I'm going to continue. Now, something forgot to install one dependency for the tool, Google Calendar. We're using Google APIs dependency. And we're going to be updating this tool to use this new initialized Auth0 AI SDK. I'm going to copy paste the code, but highlight again the differences. You can see here that we were calling the Next.js Auth0 get access token for connection. Now, what we are doing is using the wrapper that we just initialized here, we are wrapping Vercel AI's tool within our helper. And now we're getting the access token directly from the Auth0 AI Vercel. So as I was saying, we are using the wrapper that we created with the help of the Auth0 AI SDK, and we are utilizing a specialized Auth0 AI Vercel SDK to get the access token for connection. Now, what happens here behind the scenes is, let's do this now. Every time or whenever the Agentic app, when the user makes a prompt, for example, list my events for tomorrow, the LLM is going to interpret that it needs to call this tool. What this wrapper is doing essentially is verifying the level of access that this user needs to call this tool, and evaluating whether or not it needs to make a token exchange beforehand for the user. In this scenario, what is going to happen if the user doesn't yet have the access to Google authentication, to Google API, it's going to call for an interruption. And this is a new term that we are introducing here with the Auth0 AI SDK. It's a term that is actually common in the different AI frameworks that are out there, or it's getting common, is how do you introduce human-in-the-loop authorization or human-in-the-loop like actions. Well, most of frameworks are using this interruption kind of term, which basically is sending in the thread of execution of the prompt a stop and waiting for the user to make an action to then continue. In this case, for the Auth0 AI SDK, we are creating an interruption that requires the user to authorize this tool, or authorize this tool with Google, right, to be executed and get the access token for this connection. Let's continue now with the next steps, because as we're saying here, this is going to return some sort of error. This error needs to be interpreted now by our application. So this is a React Next.js application. So we have created likely some components, like React components. We're going to be installing these components now. Some other dependencies required for this. And what we're going to do now is update our chat component to handle this interruption that now the LLM is going to be returning once this tool gets executed. So going to components, chat. Again, I'm going to copy paste here, and I'm going to go over the specifics. So you can see that we are importing from the AI Vercel SDK React the use interruptions, and we are now wrapping the use chat from Vercel AI around our use interruptions with a handler. We're using this handler to basically manage the error that we are returning the error as interruption. And then we are passing this tool interrupt to our messages component, which I'm going to be updating to. So once we go to the messages component, this is sadly something that we need to do of how we built this. We need to spread this interrupt here. You can see down, we are passing this down, the interrupt down, and one more update, apologies for that, to the message component here. And there we go, here. So as I was saying, we are passing down this interrupt new error that we are creating. And now we are utilizing the ensure API access pop-up component that we install from the auxiliary AI components to handle this interrupt and display an authorization box for the user to continue. So with this done, I think I didn't forget anything. Oh, yes, I'm forgetting one more thing. We also need to update here our route to return that error from the tools, right? We are passing down the tool now, and we are executing with interruptions, right? This is a helper that we build around AI Vercel SDK to handle these interruptions. So with this done, I think I didn't forget to say files. We can run this, pm run dev, hopefully. And we should be able to access it. It's going to ask me to log in. As I log in with Google, apologies for the Spanish here, English, there we go. It's going to ask me to log in with an account. Then, yes, continue. There we go. What you see or didn't see in the prompts before for Google is that when I logged in, no scopes were asked for me. So nothing were asked for me to access Google Calendar or my Gmail account or anything like that. That's kind of also the deal with the Auxiliary SDK. Only when the application or the agent in this case needs access to any of the resources that you are owner, only then it's going to be asking you for those permissions. So for example, I can ask now, am I free tomorrow at 4 p.m.? This is going to be sending the prompt. Now the tool, which is wrapped, is going to return an interruption. This is how the interruption looks like with the component that we just installed from the Auxiliary AI components. And we can now trigger granting access to this. I hope that you see this here. I'm gonna first off zoom in and change these to English United States. There we go. So again, tell me if this is enough. I'm going to select my account for Google. This is because it's a developer application that we configure. Again, privacy policies. And after this, you can see that now I'm being asked for specific permissions to my Google account from this application. So after I accept this, this is an authorization from Auth0 because we are requesting offline access is kind of mandatory. And then give it a second, give it 2, there we go. the LLM now has access to my to my Google account and can check my availability and reply. So if I ask again, am I free after 5 p.m., now it should check again my level of access for this Google Calendar API. Knowing that now it has access, it can directly call the Google API and reply with this information for me. And that's pretty much it for the demo. What I'm going to show also before we hand the screen over is that on this repository for the AI SDK and JavaScript and Python as well, we have a full list of examples for the different use cases, the problem that we're solving for developers in outsourcing AI applications. And you can go into any of these and you're going to find different integrations with the frameworks that we are supporting right now. That's it. With this, I'm handing it over to Karanas again.
Thanks, Christian. Right, so to kind of summarize this back, we're trying to solve for 4 different use cases. We're trying to authenticate users. We're making it easier for developers that are building agentic apps to authenticate users into those apps, to have those agents call third-party APIs on the user's behalf securely without having to manage tokens. The other 2 use cases that we didn't demo but are documented and have SDKs and support and examples is when agents have to asynchronously call users to get some kind of authorization via push notification or email or something. And then finally, authorization for RAG use cases. So these are the 4 that we are trying to solve for. I encourage you all to, if you're building any kind of an agentic app as part of this hackathon, and it requires secure access to either RAG or to APIs, I encourage you to go to auth0.com/AI. Check out the docs. The quick starts describe how to solve for all of these use cases. There are some how-tos, as I mentioned earlier. And as Christian mentioned, the SDKs themselves are listed in here. So if you're building something specifically, let's say in LangChain, LangGraph, you can go to the LangChain SDK and check out the examples there. One last thing I want to call out is, so auth0.com/AI is the landing page. Then we also have some really good blog entries as an example, how to integrate MCP, how to provide authentication for MCP servers. If you're deploying a remote MCP server on Cloudflare, as an example, how do you secure tool calls that MCP server is trying to make? So there's some really good blog posts on that. And then also finally, we have a Discord. If you run into any kind of issues, if you have any questions, please don't hesitate to ask.
I hope people who are still coming, please take a seat. And hope everyone had a great session in the morning. So now I'm going to give a keynote talking about towards building safe and secure agentic AI. And as I introduced myself earlier already, I'm a professor in computer science at UC Berkeley and also the faculty co-director of the Center Berkeley RDI. Okay, great. So we are all really excited about the fast advancements in frontier AI. And this year has been called the Year of Agents. So at the same time of this exciting advancement, on the other hand, we also need to pay attention to the potential different types of risks. So in our recent International AI Safety Report, led by Yashua Banju and written by around 100 scholars from 30 countries, we list out a broad spectrum of different types of AI risks. And also I want to stress that in particular, as we deploy AI, it's important to pay attention to consider AI in the presence of attackers for a number of reasons. So first, attacker always follows the footsteps of AI advancement. Does this work? Can we turn this one on? Always follow the footsteps of technology development, or sometimes even leads it. And also the stake is even higher with AI. As AI controls more and more of the system, attackers will have higher and higher incentives to compromise these systems. And also as AI become more and more capable, the consequence of misuse AI by attackers will also become more and more severe. And hence, it's really important for us to consider agentic AI in the adversary setting. So the goal is to build safe and secure agentic AI. And largely, the problem falls into two main categories that I will briefly overview in this talk. The first one is how we actually build secure agentic AI that can protect the agentic AI systems from different types of attacks. And the second one is mitigating misuse of AI by attackers. And in particular, here I will focus on one particular domain, which is cybersecurity. So I will talk about the mitigating misuse of AI, in particular, impact of frontier AI on the landscape of cybersecurity. So first, I will talk about how we can build secure agentic AI and protect agentic AI from different types of attacks. So agentic AI systems can be fairly complex. The agents is guided by the LLM and can interact with the environment to perceive the environment and to do planning and plan for actions and so on, and then take actions in the environment. And agent safety and security is a very complex topic. So first, already itself actually has a lot of safety and security issues. And these safety and security issues get even more further amplified in the agentic setting. So in this talk, given the interest of time, I actually won't have time to talk about at the LLM level the safety and security issues. I welcome you to watch my keynote at IKEA this year, which focuses on LLM safety and security issues at the model level. And in this talk, I will focus more on the safety and security issues for LLM agents, the overall agentic AI systems. So when we talk about LLM agents, it's actually not just one thing. Actually, LLM agents has a very broad design spectrum. For example, all the way ranging from simple chatbots, static workflow, and also fully dynamic workflows and control flows. And also, actually, there are many different dimensions for this overall complex LLM agent design space, all the way including the degree of flexibility in workflow, in input space, action space, tools they use, how they handle memories, the degree of autonomy, and user interface, and so on. And the one thing I want to note is that as we increase the agent flexibility, this will also, unfortunately, increase attack surfaces. As the agent can use more diverse tools, and they have full autonomy and so on, so naturally this actually increases the risks for the agentic AI systems. And also, there are many different attack vectors under different threat models, depending on whether the attacker has access to the agents or has what type of access to the agent's internal and so on. And also, the agent's internal systems as well as the environments, they also present different types of vulnerabilities and security risks to make the whole agentic AI security issues even more complex. And when we talk about agent security, there are a number of different goals, including confidentiality, integrity, availability, and also in the agentic setting, we also have a new goal, which is contextual integrity, to ensure that the agentic AI systems, for example, tool use and so on, are aligned with users' intent and in that particular context. And these security goals can be challenging due to the different types of risks that I listed earlier. To actually achieve these goals. So in order to actually achieve these security goals to build secure agentic AI systems, we need to develop new solutions. So here I'll briefly mention two categories. One is how do we actually do a systematic evaluation and risk assessment in agentic AI. And the other one is how do we actually develop then effective defenses for agentic AI. So the first one I'll briefly talk about is developing systematic evaluation and risk assessment in agentic AI. Given what I mentioned earlier, agentic AI has very complex risk surfaces and attack surfaces, we need to develop new technologies to evaluate the agentic AI systems for these different types of risks. So here, I just briefly mentioned some of the recent work in my group and with collaborators. So this is one example, Agent Poison, which actually develops a new framework to essentially evaluate, in particular, the risks in agentic AI systems with the poisoning actually in the RAG system, putting backdoors in the RAG system. And this is another example, developing risk assessment, in particular for coding agents for the different types of safety and security risks. And this is our recent work on Agent Visual, which provides an end-to-end red teaming framework and solution for black box AI agents security evaluation. And in particular here, we develop a full black box evaluation framework that uses LLM-based solution for black box optimization and smart fuzzing to automatically generate different types of attack inputs that can be injected in the environments that the agents operate in, and using this approach to evaluate how agents may behave under these different types of malicious environments and evaluate their security risks. And here's an example of a demonstration of a real-world web agent where using the Agent Visual system, we automatically generate attacks that can be injected, for example, in online review websites. When the agents actually navigate to these online review websites, reading these maliciously crafted reviews, this can cause prompt injection in the web agents and causing the web agents to actually then visit malicious websites and then later on download, for example, malware and so on. So these are a few examples illustrating how we can actually develop different types of evaluation and risk assessment methods for this agentic AI system evaluation. However, overall, actually, doing agent evaluation and risk assessment is very challenging for a number of reasons. So first, it lacks standardization, and also there is a limited openness to do more open, essentially have an open ecosystem for the community to work together on this evaluation, and also there's a low reproducibility and so on. So for example, a lot of the recent papers actually is difficult for others to reproduce the results and so on. So to address these issues, I wanted to briefly mention that we actually have right. So we are launching a new platform, open platform called Agent Beats. It's an open platform for agent evaluation and risk assessment that's designed to address the challenges that I just mentioned. Agent Beats provides a standardization for essentially different developers building agents, building their own agents, their own environments, and so on, to all actually easily get connected in this open platform, the Agent Beats platform, and using the current widely adopted open standards such as A2A, MCP, and so on, and provides a unified SDK for all these to connect together. And also provides openness, where the community can contribute public agents, benchmarks, and hosted environments, and so on. And also this allows full reproducibility. When the evaluation is done, everything gets logged, gets traced. So this also enables essentially automatic tracing, multi-level trace logging, and so on. And also the platform is designed to be easy to use. So it's very easy for developers to actually save the developer a lot of time to actually build agents or environments to connect into the system. And we already have a number of a very rich integration already, including different types of web and coding agents environments, and also different types of attack agents, including prompt injection, jailbreak, and so on. And Agent Beats supports broad different types of use cases. You can use Agent Beats to run agents on popular benchmark for evaluation. You can actually compete, rank your agents on public or private challenges. And you can contribute by developing new benchmarks, environments, and agents to connect it to this open ecosystem and collaborate with others to improve our agents and so on. And Agent Beats supports many different types of scenarios, including single agents and also multi-agents in many different settings. So the goal is, and also the hope for developers, that this will be very easy for developers to use, to set up your agents, and then to run and evaluate the different settings. And you can launch competitions very easily as well. So we welcome you to go to agentbeats.org. You can sign up there and stay tuned, and also to help contribute. So that's for evaluation and risk assessment. And for defense, agentic AI defense, I would say, is a huge open challenge currently, given all the complex risk issues that I mentioned earlier. So first, for agentic AI defense, we need to have, we strongly recommend a set of principles, including defense in depth, least privilege and privilege separation, and also safe by design and secure by design, and ideally to provide privilege secure solutions for agentic AI systems. And given the interest of time, I won't be able to go into all the different types of defenses that we need to actually develop and adopt in agentic AI defense. Overall here, so I list at a high level, essentially we need to develop different type of runtime protection, also different secure design methodologies. We need to have a stronger, develop better access control, and also hardening at different levels of the systems. So again, given the interest of time, I won't be able to go into the details here. So we have an overview paper that's coming out soon that actually goes into detail on this. And here I just want to briefly mention as one example of some of our recent work on, this is an example of Project, which is a programmable privilege control and guardrail solution for our agents that can automatically actually generate security policies to help protect agents in different settings. And also I wanted to mention that we have another session specifically for safe and secure agentic AI in the frontier stage in the afternoon as well. And I welcome everyone to check out more there also. And right. So this is the first part on building secure agentic AI. So I want to now quickly go into the second part about mitigating misuse, in particular in the landscape of cybersecurity. So as I mentioned earlier, with agentic AI, there's a broad spectrum of different types of risks that we need to pay attention to. But in particular, I do strongly believe that cybersecurity will be one of the biggest AI risk domains. Attackers have diverse incentives for attacks, and we're already seeing today huge damages from attacks, and increased AI capabilities, in particular in reasoning and coding and so on. They can significantly reduce attack costs and increase attack scale. And also today, we're already seeing that Gen AI has caused order magnitude increase in certain types of attacks, such as social engineering and phishing attacks and so on. So the key question here is, how will frontier AI change the landscape of cybersecurity, given that AI do use nature? So the key question here is, given that AI can help both attacker side and defender side, who will AI help more, the attacker side or the defender side? So in order to address this question, we need to do systematic investigation for the whole, across all the different stages of a cyber attack, and also looking at its defenses. So with our recent work, we have set out to explore this area to in particular investigate this question. So my group and with collaborators, we were actually the first to investigate about using deep learning for program boundary analysis and vulnerability detection many years ago. And even back then, we showed that deep learning actually can achieve state-of-the-art in certain domains, such as binary code similarity detection and vulnerability detection and so on. And fast forward now with the LLM, the AI capability is significantly stronger. So in our recent work, we also evaluated and investigated hundreds of recent papers exploring the current AI capability and impact levels in the different attack stages. So the current work, with our work, it showed that currently, except for attacking humans using phishing, social engineering attacks, and so on, the attacks, the AI capabilities on the, in the other attack stages are still relatively limited. But however, our recent work shows that this is changing very fast. So in two examples of our recent work, we show that actually now, today, AI agents actually can already be very powerful in cybersecurity space. So one is Bounty Bench, where we developed a benchmark from using real-world bounty tasks. So here from like 40 different actually bounty programs and so on. And our work showed that with the latest model, and even with the relatively simple agents, actually these agents now can solve these, some of these real-world bounty tasks, including finding vulnerabilities and patching vulnerabilities as well. So this is in the web application domain. And our work showed that actually agents today, they can actually solve these bounty tasks equivalent of tens of thousands of dollars. So essentially, these agents can already make money by solving these bounty tasks. So that's Bounty Bench. The second one is CyberGym. This is on large scale, real-world, widely distributed open source programs in C, C++, and so on. So we developed the CyberGym benchmark with close to 200 these large-scale open source programs, which have around, the benchmark also includes around over 1,500 known real-world vulnerabilities. So the task is to see whether agents can find these known vulnerabilities, as well as actually whether the agents can find previously unknown zero-day vulnerabilities. So the work showed that actually, again, with the latest models, even relatively simple agents can actually do a lot. And they can actually solve close to 20% of these, actually find close to 20% of the previous known vulnerabilities, and also actually can find 0 days. In particular, we discovered 15 0 days, and also a number of CVEs have been issued based on these 0 days already. And the CVEs actually are attributed to CyberGym, which is nice, to these agents. So what I just showed is that AI is improving really fast with the current agents. Already they can, already they have strong capabilities in cybersecurity. And in particular, on the attack side, the question is how can we actually develop better technologies to use AI to more help on the defender side. So there are a number of challenges here. So one is what we call equivalence classes. So whatever we develop in general to improve on the defense side, the same technology can be used to help the attacker side. And also there's natural asymmetry between attacks and defenses that makes it actually make AI to help more, help attackers more than defenders. So for example, on the offense side, you only need to find one attack that works, but for the defender, essentially you need to fix all bugs and prevent all attacks to succeed. And in our paper, we analyze also different types of these asymmetries between attacks and defense. And given the importance of this domain, we also recently launched the what we call Frontier AI Cybersecurity Observatory that provides an open platform to have the community to come together to do continuous monitoring of the AI capabilities in cybersecurity space. And we welcome others to join this effort as well. So then one key question is then what can we really do to actually shift this balance to help AI to help defenders more than attackers? And as I mentioned earlier, some of the defense solutions, such as trying to find bugs, are also for this reactive defense where try to detect attacks once attack happens. These actually still can have AI help attackers more than defenders. What we propose here is to actually use the paradigm for proactive defense with the secure by construction, where we can use AI to actually try to build properly secure systems. So many years ago, actually quite a few years ago, my group and with collaborators, we were among the first to actually use deep learning to try to automate theorem proving. And this is a paper with Ilya from OpenAI back then. So back then, we showed that deep learning actually can help automate certain steps in theorem proving, but it was limited. But now, fast forward with the recent advancement in AI, we do strongly believe that we are hitting an inflection point where we can develop frontier AI technologies to actually help with formal mathematical reasoning and automate theorem proving. And you can check out our paper here. And then using this approach, we hope that we can develop agents. Instead of just playing games like Go, we can actually develop proof agents that can automate theorem proving for program verification. And then when used in conjunction with program synthesis, we can automatically generate not just code, like today, we can actually generate provably secure code. And for more information, you can, given the interest of time, I won't go into the details, but for more information, you can check out my IKEA keynote, as well as my lecture in the Agent MOOC last semester, on a 2-hour lecture on actually building safe and secure agentic AI. And also, if you are interested in participating more in the efforts for frontier AI impact in cybersecurity, you are welcome to sign up here. We'll be organizing workshops.
Everyone, so happy to be here to kick off session 3 with you. I'm not Deepak, as you can see, but he did ask me to come here in his place. My name is Adam Kaplan. I'm a senior staff engineer at LinkedIn. I work on Agents platform, which is part of Core AI, where I work with Deepak on the future of autonomous agents. So just a quick sidebar, why LinkedIn? Why am I here? LinkedIn's vision is to create economic opportunity for every member of the global workforce. And we believe that we can't do this at this point without agents to help workers unlock value by getting their work done more efficiently. So I promise this is not a producty thing, but bear with me for a minute. There is a point. Late last year, we launched something called Hiring Assistant, which is a multi-agent product that's targeted toward recruiters, so probably nobody here has used it. This is not the target demographic. But this is a system which uses 4 agents with a supervisor agent, kind of a common pattern. I know everyone here is probably familiar with it because I saw that in the previous talks, hands were raised. Like pretty much everyone has designed a multi-agent system here. Well, as pre-work, we start out with a preference model that's constructed by analyzing the recruiter's decisions and actions made in past projects and current projects so that the agents can be personalized to a particular recruiter. And so these 4 agents here, the first intake agent, that's helping the recruiter get through the workflow of creating these roles and job descriptions. The sourcing agent goes and finds a huge list of candidates. The evaluation agent helps you hone in, helps the recruiter hone in on the best candidates. An outreach agent actually initiates that initial communication to the candidates in a way that's personalized to the candidate and the recruiter. So this system is supported by a deep ecosystem of tech stack that consists of like open source and sort of where there are gaps in the open source ecosystem, some home-rolled technologies. So why am I talking about this besides to show that we're doing cool stuff? Hiring Agent was shipped in October. That's a multi-agent system delivering value to our recruiter customers for months now, and the reviews are that they're getting significant positive impact. So when we talk about the frontier, this is the frontier stage. Multi-agent systems certainly are the frontier, but I feel like this is like a crashing wave at this point, not a cresting wave. So when we're standing on this frontier and looking forward, I mixed my metaphors here around the curve, but when we're looking forward, we see autonomous agents rising in importance. And these two things are linked, right? And I'll get to some of that in a moment. So what is an autonomous agent, at least by my definition of an autonomous agent, is an agent that starts to take in multiple signals from its environment and use those signals along with its memory to orient itself. And then we go into the typical React loop that you can see there on the right side, reason about the next best action, take that action with a tool, incorporate the feedback, and on and on. So it's a subtle difference, but very impactful by taking in multiple signals. We're going to get into a bunch of interesting problems that I want to talk to you about here. The first one is memory. Okay, so again, this is a typical memory stack that you might end up with if you're designing an agent within a multi-agent system or not today. You have roughly 3 tiers of memory. The first is your in-session memory. This is your active conversation, messages that the user sent, what you sent to the message, tool calls you made, results from those tool calls. Very high resolution. The second tier, when you have too much of that conversation, is summarizing that history along some axis of classification. If it's like a ChatGPT where you click new chat each time, then there's your classification right there. You summarize each of those. And now you have, in your context, you have the broad strokes of what you've done and the learnings and takeaways from that. When you have too many tasks that have been summarized, now we move back one step further, break everything down into primitives, facts, phrases, shove them in some retrieval system, EBR, or if you want to be fancy, maybe something that's powered by an agent, or maybe a combination of those two, and use it for RAG. So with an autonomous agent, it starts to look a little bit more like this. If you can take in multiple signals at once, and I'm talking about a specific agent here. I'm not talking about everyone's individual agent, right? So those signals can come from 2 different users. So now we end up with these 2 isolated memory stacks. They're isolated because people expect that. There's a certain lack of trust we all have right now, everyone in the world, with agents. And part of getting around that involves us assuring people that when they say something to their agent, it's not going to be repeated back to another person or otherwise, leaked across boundaries. But this presents a pretty big problem, and it was touched on in some of the morning session 1 talks. Take a straw example. If we have an autonomous agent named Evie who is working with a user named, let's say, Jane, to plan an event, it's an event coordinator agent. And it's working on setting up all the logistics for something like this conference. And then we have another person, John, who's aware of that whole setup and reaches out to Evie and tells that agent, hey, we're going to need 10 more rooms or something. What is that agent supposed to do? In the current scenario, the naive context, it's probably going to start to reach out to the hotel, let's say, I mean, if that was possible. And that can cause confusion because now you have not one single point of contact for that, making those decisions. So the way around that is to introduce another type of knowledge, which I'll call here common knowledge, for that agent, within that agent, where it's aware of at least what it's doing in other contexts, if not just enough information so that Evie would know that it shouldn't take an action. It should probably tell Jane that there was this change, and maybe we incorporate that information into the main task loop instead of working somewhere and causing chaos. So how do you get things into common memory? We're working on it. That's about all I can say there. It's a big one to solve because the concerns that you would have with this are very broad. There's trust concerns between those 2 users. If you're in a company, which is likely where this would be happening, there's regulatory concerns about data being shared, like DMCA and things like that come into effect. There's policy concerns from the enterprise administrators. Lots of things that need to be worked through. And then there's the basic human expectations of what is appropriate to be shared. But I think we can solve this. And the reason I think we can solve this, and first of all, we need to solve this, because if we don't solve this, our agents are stuck in boxes. and it's going to be a pretty lame next 2 years. The reason I think that we can solve this is because human memory, we usually experience human memory through language. Like there's actions that you take, but I think that's not really the analogy we use, because if somebody forgets how to use a spoon, we consider that a debilitating illness, right? That's not what we're talking about here. We're talking about how people make decisions about what memory is appropriate of their memory is appropriate to use in what context, and how to let it decay, in these tiers, how to let it decay in this sort of expected fashion. If you can't remember what type of pencil you used to take notes 2 years ago, nobody thinks that's a problem. It's a feature of the system. So because we can express those limitations and boundaries in language, I think that starts to look a little bit more like the reasoning problem. Once we were able to express reasoning through language, we could attack it with models. Oh, that's something that I'd like to see happen here, and it's pretty important for us. The next place that I want to go is to talk about our modular agentic architecture and how it's essentially come together in practice. So we start here with our sort of typical React loop that I showed in the beginning, with an additional box here in the top labeled tool discovery. So the tool discovery is meant to help the autonomous agent explore its environment. So with specialized agents, you tend to have not much agency. There's a few tools that they have. There's a sort of predefined workflow that they're operating in with set decision points. And they make decisions, the LLM's making the decisions, but where it goes is kind of controlled. When you have the more autonomous agent, it has a larger set of tools available to it, just by definition, because you're doing the work of multiple smaller agents. 2 years ago, I think maybe 10 tools was the guidance that you can realistically put into an LLM. Last year was 30, this year with O3, we're at 100 for that particular model. Great progress, 10x in a year and a half or so, but the amount of tools is 1,000x since then. And we see things like MCP on the scene, providing this fabric that allows existing APIs to communicate their capabilities as tools to LLMs more efficiently than ever before. So there is an explosion of tools. Tool discovery is going to be with us for some time now, for some time yet. Yeah, I'll leave it there. Now, ACT, tool calling. When you have the more autonomous agent, where you're not planning every single action that the agent takes, you will quickly realize that there are two classes of tools. Idempotent tools like knowledge retrieval that are fine, you just use them. That's maybe like 10 or 20% of your tools. And the other 80% are destructive, potentially destructive tools. Sending an email, they're all like communication-y, right? Sending an email, committing code is communication. Sharing a doc, commenting on a document, or like planning an event. So these things, because they start looking like communication, we found that we have to treat them the same way we treat messages sent to the user. So we have safety validations on the parameters that go into the tool to make sure that they're not hallucinated, that they're appropriate, and things like that. Similarly, when we get feedback back from the tool, we don't just stuff it in the context. We first have to do some anti-jailbreaking and other checks, static and model checks, because once data goes into the context, it becomes very difficult to take it out. You might get saved by, if you're in Azure, by their content filter, for example. But then what do? It's hard to back off an agent that's working on a long-running task to get back to a state where you can actually like execute safely, because there might have been tool calls that happened in the middle that you can't forget. So both of the feedbacks from the tool safety and the jailbreak are communicated, both of the validation feedbacks are communicated as tool feedback, so that the autonomous agent can reason about what happened and make a decision. For example, maybe it goes and tries to find another tool, or maybe it changes the parameters it uses, comes up with a novel way to reach a conclusion, or gives up. And the last thing that I'll talk about here that we found becomes very important is that there is not enough GPU, right? Okay, so reasoning models are great, and you can make some amazing experiences quickly with them, but you can't scale them. So what we found is that there are a pretty significant amount of user requests that come in, which can be satisfied by the existing context. You don't need tool calls. Your basic, like if I asked the agent what its name was or whatever, something like that, which it just needs to reference in the current context and respond back in a coherent way. We use a completion model for that. So by doing complexity classification, we can move work off of the slow, expensive reasoning models onto the faster, lower latency completion models and let our reasoning models spend more time on the harder problems. So in essence, what I want to just leave you all with is that main takeaway that I've had after working towards autonomous agents for the past 2 years now is that if you set out to bend the human expectations in the human world to the agentic world, you're not going to succeed. The way forward here is to take the agents and take the systems that we're building and adapt them to the human shape. This world is designed for humans. Everything about it, the expectations, the communications, the way we work, is designed for humans, and that's what we adapt to. So, I mean, my last minute, something that I've been thinking about recently around trust is like people expect the model to be perfect, never leak info. Okay, when you hire someone, you onboard them into your organization and give them the keys. And why do you expect them not to exfiltrate all your data? If we can understand the behavioral psychology of that and figure out how to adapt our agents to that, to build the infrastructure for them to conform to that, I think we're going to be very successful. So thank you. That's all I have for you.
I'm Ashutosh Nemo, consultant data science at Dell Technology, where I lead design and development of Gen AI systems at scale. The topic that we are going to cover today is from hype to impact, right? And it's a bit different than the topics that we have covered till now of agentic application. It's more about how do you bring agentic applications to scale or to production, right? Because it's all the hype right now, but getting it to production is what's the difficult task. So starting with the market, right? We have seen, we are all live breathing Gen AI evolution day in, day out, right? We see models coming in, research coming in almost on a daily basis. It's hard to keep a track of what's going on, and so is for industry, right? Industry struggles with legacy systems, with all of the data problems and all of those things, right? One of the survey that was conducted by Big Fours, right? What that led us to is 95% of the companies and Gen AI leaders are talking about bringing agent tech and Gen AI into the companies, but only, if you see on an average, only 20 POCs make it, right? And within those 20 POCs, only 30% of it graduates to production. So what's causing this lag, right? The research further suggested that strategic misalignment is what's causing it, right? So when we think of Gen AI or agentic systems, we think from a shiny perspective, but we fail to miss the mark of is it actually adding the business value or impact, right? Is it actually usable towards the end goal? But regardless of that, wherever that makes a green light or wherever it's able to go to production, you can see that it's a net positive, right? So the path or the goal at the end of agentic system is clear that there is value out of it, but what are the roadblocks and how do we navigate it? So if you see current challenges that are in agentic adoptions, right? There are strategy and operational challenges, which as I stated before, with strategy misalignment, but also with matrix stride flow, right? Currently model, if you have a machine learning model in production, it's being monitored by business day in, day out. There is a KPI attached to it. You cannot miss that mark any day. So those are the business constraints that are in there, right? Companies are struggling with, should we build versus buy, right? That's a big discussion going on right now. Everybody thinks, should we do this POC or should we buy it? From a developer and user perspective, as the technology is growing, nobody can call themselves a master of agentic AI at this point, right? We don't even know what's going to come out tomorrow. So there is definitely a skill gap even with the pros. And at the same time, we have legacy systems, legacy data. It's hard to move those bottlenecks sooner at the rate at which the technology is advancing, right? Now with Gen AI, there is a huge difference between the pilot and production phase, right? As the users are evolving, everybody is using Gen AI, getting used to it, there's a huge gap. So let's say, for example, we tested out a search bar which could go to a product page, like you have it at Amazon, right? Before the reviews, you could just go and search anything related to that product at that product page. We tried doing that and add a fancy Gen AI-enabled name tag to it. With pilot, it worked very beautifully, right? People were able to search what they needed with their product. But when it went to production, what happened is folks were trying to prompt engineer the search bar. So the expectation is different. When they see Gen AI, people have all of different sort of expectation of what Gen AI can deliver to them, right? So those are the constraints under which agentic AI systems are there, right? And then the cost, latency, and safety and evaluation, these are the bigger challenges that are needed to be solved there. Evaluation is an active research space. These are stochastic processes. We don't know how to evaluate it. We are all used to having a deterministic accuracy number at the end of it, right? So these are different systems. But given all of that, right, how to get started or how to get kickstart with one of that POC that could help you cover the first mile and could deliver value to your business. So start targeted and modular. Take any existing process, break it down piece by piece, figure out friction processes that are existing between the system, right? To those, let's say, I'll start with an example, right? Let's say you have an NLP model where the input is text data and the output is labels that are coming out of it. Think, could the input data be reformed with LLM? Could you pre-process it so that the NLP model can make a better prediction? Could the predicted labels, could they be enhanced or augmented in some sort of manner for the user? Now that starts your LLM workflow, right? When you think of it, you combine this LLM workflow, you add a planner agent to it, you add orchestrator, you add validator, that gives you a task-specific agent. When you combine multiple of these task-specific agents, that's when you get your agentic AI, right? So in terms of thinking from an existing production system perspective, think in terms of block. You start adding block by block. What these blocks will also enable you is think in terms of evaluation when you're adding a block, right? It's hard to think after designing a system of how will I bring in safety? How will I bring in evaluation? All of those things, right? So go from an LLM workflow standpoint to an agentic standpoint. Think about augmenting first and automating later. When we think of agentic AI, we quickly think that, okay, this is where we can just replace a human. We are not at that stage with agentic systems, right? What we need is, we need to augment it first, make it easier for a human to use. Once the trust and users perspective builds in, that's when we can start automating it. Iterate fast, but keep safety in mind, right? Also, choose a hybrid model strategy. One model is not going to work for all of those things, right? Choosing a big reasoning model at all places, even for smaller validation, doesn't work. These are the constraint and enterprise environment. We have limited set of models available out there, right? With open source, when we are experimenting at our own pace, that's good. We can pull in any model from Hugging Face and play in. That works. But with enterprises, that's not the case. They're very restrictive in what models are available, how you can scale them, how you can use them. Think from a hybrid model strategy. These are the things you need to. This cannot be retrofitted, right? So these need to be planned ahead when you start with your POCs. Again, the last point, score by impact, not by shine, right? Make sure that those agentic are actually adding business values at this point. And all of the points that I'm covering here, these won't help you build the best agent, but will help you build the most reliable, human-friendly, more of user-friendly, and help you get a business buy-in, right? Once you get that business buy-in, that gives you a momentum to get actual agents to production. So you got started with POC, right? Now what next? How to go to production and what to keep in mind. So when taking any agentic POC to production, right? Think about memory. Memory will play a big role with this agentic systems, right? If you have a lot of agents working throughout your system, you'll need to start off thinking memory as a service layer. It needs to be short, long, episodic, all of those kind of memories, because each agent will be needing its own requirement. Think from a workflow design perspective, right? As I said, it's stochastic processes. So we need to put in strategic deterministic things in place. It could be a validity check. It could be an LLM, it could be a machine learning model in place, right? All of those things. Think from a term of model fit and mix, right? It doesn't make sense to overkill agentic solutions, right? Although adding a reasoning model won't solve it. If agents are not, if it's not able to do it, it could be replaced with something else for now. And when the models graduate, we can take it to the next level, right? From scaling and enhancement perspective, think of context engineering. Now, this is a bigger challenge. When we work in POCs, we think of, let's say, I'll take an example of few shot learning. With few shot, you might have 10 examples in your POC for an agent to perform, right? But in production, that 10 examples, running it every time will cause latency, will cause more compute. That compute could be used for reasoning or some other purpose, right? So think of context engineering. Could those examples be shortened by run specific, narrowing it down to what's useful, what's not, right? So think from a context engineering standpoint, think of agent ops. Agent ops is a totally new thing that we need to consider. Classical MLOps was one, but now using E2A standard, MCP standards, all of those things, how your agent is communicating outside, inside, all of those things. Tracking telemetry of the model is again a new thing that's coming out. We need to monitor each tool call, each thing, each step that was executed. It's becoming more and more important to debug the systems, right? Think from knowledge boosters. So all of these LLMs by itself are good at at answer generation, right? When we make it agentic, we make them good at decision making. But if you want to make that decision in terms or context of your domain or your enterprise solution, that's when added with search and adding a knowledge graph to it gives it a context awareness, right? So think of it as a human brain. How will you think? We have everything mapped out. Till the agents have things mapped out, making them grounded to your enterprise solution is difficult. So this is like, let's say we talked about how to get a POC running. We talked about what to consider for production. Now how to make sure that your teams are evolving from POC to POC, right? Because let's say you built an agent today, would be outdated 6 months from now. Will be new LLMs coming out, more capability, more rigor. All of your agent could be just solved by one LLM if we think that way, right? We don't know, and we need to build that strength or resilience in our teams that we keep on evolving from POCs to POCs. Think of internal benchmarking, right? So whenever we develop a POC, make sure that you have your own data set specific, prompt specific, LLM specific, what is the performance. Now where this will help is in terms of productionization, somebody might need to come in and debug that prompt later. Currently we debug the code same way, right? And you might not be there. So who makes sure that why this prompt was written a certain way? Because it's all feelings out there. So we need to make sure that there is a structured process of tracking it. What benchmarks was it evaluated on? These necessarily not be external, but your industry domain specific benchmarks, right? Design for reusability, make sure that even though one of the POC that you do fails, there are plugin modules that could be reused to other POCs, right? Like, for example, you might have had a search capability built in. That search could be expanded to other POCs. Think of those manner. If you developed a validator agent, can I pick it and put it in some other agent? Because everybody will be building agents, planner, validator, orchestrator. These are some components that will jump in from agents to agent, right? Think of it from modular perspective. Having a human-centered design, right? Again, we are automating things for humans, not replacing humans. So we need to think from that manner, right? It's more of a co-pilot that agentic systems will bundle. At the same time, thinking the UX, UI from agentic perspective is also needed, right? It's not the traditional clickable UI that we all had. It's more interactive. How do you enhance that UI so it builds trust, right? Let's say an agent is reasoning and going to a step. How do you make sure that those reasoning steps are communicated to the human? So there's a trust built in, so they know, okay, agent thought this, and hence it's went there, right? That's more of, if I would have done it, why would I have done it, right? More of those kind of things. So with that, this is Dell's example, right? That's where all of the learnings that you're seeing are coming from, like Dell's next best action. It's a recommendation engine for troubleshooting that we have in-house for our internal agents, right? It helps to get customer support faster. It recommends them what should be the next action given a customer reaching out, right? It's the same process we had, if you see, we had a ML model and baseline. We had a matrix tied to it. We identified frictional gaps, rapid experimentation, right? That gave us learning and feel of the system of what LLMs are, what tool calling is, how many tool calls do we need, what is the complexity of tool call we can attempt, right? All of those learnings. Once we had those learnings, we combined those and decided on the experiments that we can go forward, which align strategically with the business, right? It may not be fancy. If a simple summarization solves it, why do you need to build a rack for it, right? So those kind of things. And again, when this POCs graduate to production, we thought of it from both enhancement as well as augmentation perspective, right? Enhancement meaning it could be plugged into the system, but augmentation is, could it be assisting the system further? Could it take to a new journey or new use case for the user, right? With that, we were able to achieve this seamless integration into production. The system is being used by 10,000 plus agents throughout the globe, leading to at least 10% reduction in time for solving each case, as well as reducing repeat dispatches and making the flow more easier. So that covers my talk. Thank you.
And it's how to build agents for chip design, hardware agents. A little background to see what we are doing here. I'm a professor at UC Santa Cruz. My background is computer architecture, so chip design. but I always have been doing how to improve the productivity. Obviously, that includes design, verification, different aspects of the chip design. But today the focus is AI agents, how to build agents to help me improve productivity at this globe. Now, obviously, this is a work for a lot of my students, myself, that's my Git commit history. I like to work too on the code. So what's the goal? Because I think it's important we set the goal, what I'm working about. So the idea is to improve chip design productivity. And this includes the coding, the verification, a lot of effort on optimization parts. And there can be some cloud, either CLI kind of interface, and this is something we are working on. It's not how to integrate AI on the EDA tools. There's a lot of people working on that area. It's a different community. Here is how to improve the productivity, much more like what we are talking here at the conference. Because it helps you to understand how do I approach the problem and what do we do. I think it's important to, what is my view on LLMs? How do I see them? How do I use them? In a way, they are sort of an alien intelligence. So they are better than humans in some things. So they are better as excellent translators. So they can translate to English, French, much better than me. They have excellent recall, or not excellent, but very good recall, much better than humans. But in some way, they are worse than humans in consistency. They have maybe not very good term, but funny failures. They have many strange failures that you have. So how I'm gonna make it work with this? Well, the first thing is I'm not going only the LLMs, I'm building on agents around. So the agents, I tend to call it many times grounded agents. I tend to call it more verifiable agents whenever I can. The idea is that we always have coupled the LLMs, whatever we use, with checks, and whenever possible, we verify. In hardware, we can verify many times the results. So what we keep doing is building pipelines in which you can have an output of the LLM, and then you check if the result is correct. If not, you keep going back and you keep iterating. Because we have these verifiable agents that we can build, so we can iterate and go towards a better solution. So we check with the EDA tools whenever possible, like do we have mistakes, like combinational loops? Do we have things that they shouldn't be happening there? And if we have a verification infrastructure that usually in hardware you tend to have it because it's very expensive to do a mistake. So then you can check with the verification infrastructure. Whenever possible, you validate with previous results. Many times you are doing optimization, you are just transforming the code to get better quality code. So in that case, we can use formal tools to formally prove that the code is equivalent, even though they look very different. So at the end of the day, there are many blocks, and it looks like a compiler. So you have blocks that have the typical React loop, so you can have some reasoning to expand. You might want to extract inputs and outputs. So, and you have a compiler-like flow. So what makes hardware special is that it doesn't work with a normal, Python is a von Neumann architecture. Hardware is not when you program hardware. And there are many issues. Not von Neumann, pipelining is a very specific way of parallelization that the LLMs don't have very good training and they do a lot of mistakes. And there are a long list of the slightly different on the programming language. But for the non-hardware people, I have a little slide. So if you were having a program like this, you say the result of C is the result of multiplication A and B, and then you write assert that C is the result of the multiplication, and let's assume that this does multiplication. In hardware, this can fail. And the reason is because the result might not be this cycle, might take 2 or 3 cycles later. So there are a lot of checks that you might have to do that the code generation on the LLMs don't have that assumption because there is not enough training set for these type of languages. So how do we do? Because it's a short talk, I'm just going to show you a high-level view what is the idea. So we have 2 programming languages. One is Verilog, the other one is Chisel. So how do you do a reverse pass? So you can build a compiler-like infrastructure, putting the LLMs in the middle to solve this, and at the end there is no hallucinations because you formally prove that the result is correct. So what do you have? You have original Verilog, you have a fixed Verilog, so you have a change, and the original chisel. You want to have a patch on that chisel. Now, the first thing, you have to narrow the space because those files are gigantic. So you do a diff, like a fuzzy grep kind of thing. Then you can start to filter per tokens. Then you match where is the likely sources. You have to guide the LLM because you provide the whole thing, it's not going to work. You provide likely sources where you have potentially problems. And you have a hint of database of things that you have been solving before in similar experience. And then you generate many patches. No, just not to fix one, you generate many, and you change the temperature, you try to play to the different variations. You compile and you have a React loop. Then you LEC is logical equivalent check. It's a formal equivalent tool pass, so you can formally prove that they are correct. And then if it gives you the answer, you know, I fixed the chisel and it's correct and I don't have any problem. Now, if it doesn't give you an answer, then it's like, well, let me expand the search, let me try it. But at the end of the day, you may have IT bug. So how does it look when we try with different LLMs? So it depends on the results, but around 80% of the time, we're able to fix the bugs. We're still working on the type of bugs because the question is how do you add the bug? Many of the bugs, we change the Verilog, but then we, as humans, we don't even know how to fix the chisel unless we blow up all that section and then suddenly we start to fix. So many of the bugs that we have added, we don't know how to fix them. So we have to see what is a fair comparison. But in 20% of the time, we say, no, sorry, we cannot fix it. The idea is that this is just an example. There are several other flows that we are building like that. Different flow, different pipeline, different idea, but it's the same. So what are the things we are having? We're working on open source, so you can check it, but because we are as active research is careful with the repository. You need to have on this is our second version, because in the first version, the students were doing a lot of benchmarking, consuming a lot of tokens. And things that we did is like we start to put incremental step parts. We enable caching. The steps are hermetic, help us to debugging. So we are working on the Docker integration. So there are a lot of little things on infrastructure that makes the thing more useful. And we have some other work in progress. If someone is interested in talk to me later. But we are trying to look at things like Verilog format, formatting Verilog, improving frequency. I have 2 students working on this. And the debugging loop. So you have a long verification and then debug it. One thing that is a challenge for our community is that the tools are very slow. So the incremental part is a challenge for us. Like, as a reference for people who have not used synthesis tools, it's not uncommon, it takes 48 hours to compile. So to give you the GTS, which is the final result before the chip to get information. So it's a very slow flow. So in conclusion, we are working with hardware agents, exploring chip design, still deciding how to interface. I keep playing with different things. I keep using cloud code, like MCPs. I think the way is to go there, but we're still not convinced how to break down the pieces or not. I'm searching for collaboration and feedback, and if you want, send me an email. Thank you.
Thanks for the great talk. Yeah, our next speaker will be Risto Mikulainen, who's a professor at the UT Austin and the VP of AI research at the Cognizant AI Labs. Yeah.
Coming up. Okay, good. I'm going to talk about a particularly interesting technology that has come of age, especially in the context of AI agents. And this is work that I've been working on for decades, but most recently at the Cognizant AI Lab, which is right across the bay. So the motivation is that AI has actually matured from being a tool from imitating what people do to actually creating new things, to making decisions, becoming agents. And the question is then, how can we discover creative decision strategies. It doesn't come from gradient descent. I mean, that's imitation. And even reinforcement learning is really climbing the nearest hill. You have one individual, you try to incrementally improve it and get to the top of that hill. But there's limited amount of creativity that you can establish that way. This is a challenge that creative decision-making has faced. There may be many different strategies, and they be very different, and each one of them good in their own way. How do we find the good ones? The space is really huge, the space is really large dimensional, and it's deceptive. So the solution is population-based search, also known as evolutionary computation. The idea here is that you have a lot of individuals, the whole population, and it's spread out across the solution space. And it's not just a bunch of individual searches, they talk to each other. You have crossover that allows you to recombine two good solutions in order to find something that's even better. For instance, this one crossed over with that one might give you that peak. And surprisingly, this actually works really well. It scales up really well. In high-dimensional spaces, for instance, you can solve problems with 1 billion variables. Remember, humans can handle maybe 7 plus minus 2, Bayesian optimization maybe 10 dimensions. This is 1 billion variables. Kalyan Moydab on metal alloy manufacturing process showed that. Also very large search spaces, where there are potentially 2 to the 70th solutions. That's like a multiplexer design problem of 70 bits. Hormuz Sharzad and Baba Kodjet showed that you can solve this using evolutionary search. Just to get you an idea what that number actually is. 2 to the 70th looks pretty compact. If you write it out as a decimal number, it takes light 95 years to go from the beginning of the number to the end of the number, 10-point font. So that's how many states there are. You can still find solutions because these searches talk. You find a partial solution, another one in this population maybe finds another part of the solution. You recombine them, and this way you can make progress and find solutions in a space that's large. All right, so, and for deceptive spaces, there are techniques that we've been working on in the evolution computation community for decades. So we can find surprising solutions that are also useful. Now, evolving neural networks is a special case of population-based search. There, our population consists of encodings of neural networks. Most likely lists or trees, something simple that then decodes to a neural net that we evaluate in the environment, and that becomes the fitness of each individual. And then we recombine them using crossover and maybe mutate them to find new kinds of DNA. This way we can discover solutions that are complex, creative, and customized to the task. So this is actually a visualization of a neural network that was discovered this way to control a robot in a competitive foraging and pursuit evasion task. So that's neuroevolution, applying evolution optimization to neural networks. Now, let's get to the agent strategies. So in the real world, what we would like to do is evolve a neural network that takes the current problem or the context as input and produces actions, the decision as output. And then we'd like to do it in such a manner that this neural network, this decision strategy, optimizes the outcomes. It might be, for instance, rehabilitation or treatment of a disease or marketing strategy or something like that, a decision strategy. Now, in the real world, it may be dangerous. I mean, you don't want to experiment different decision strategies on people, like what drugs to prescribe for a patient. You want to have a surrogate model of the world. And here we can use standard machine learning. We collected a big data set of decisions in the past. For these situations, this action was performed, this was the outcome. We can train a model, just plain neural network, to imitate that data. That's the imitation. We know how to do that well. Once we have the surrogate, then we can evolve a neural network. Each time we have a candidate, we don't put it in the real world. We ask the surrogate model, how good is this decision strategy? And this way we can quickly evaluate millions of different decision strategies in order to find the good ones. So this is the extension to current AI. We are not just predicting what will happen, which we already know how to do, but we also figure out what we should do about it. That's the new AI. All right, so a couple of examples of that. First, designing websites so that we have optimal number of conversions. You go to this site and you're really compelled to press this button, find my program. That's a conversion. And this is a real-world application. It actually is running in the world. This was designing the widget here, the sign-up widget for this website that advertises educational programs. And it was actually evaluated in the real world while it was searching. And the professionals who designed these websites called this approach the ugly widget generator. Because to them, these widgets look ugly. They did not adhere to design principles, which are, for instance, common colors and all kinds of simple things like that. This is what the humans came up with. It's much more boring. This one is much more on your face and something that converts actually 45% better. So this is what is the running theme of this AI-based evolution population-based search. It discovers solutions that humans miss, and they perform better. Another example is in cyber agriculture. This was a collaboration with MIT Media Lab, Caleb Harper. They have computer-controlled greenhouses, or they're actually containers where you control how much light goes in, what kind of light, temperature, nutrients, water, everything is computer controlled, and we don't really know what to do. Farmers know about their land, but not in general what you should do. So we evolved growth recipes, and actually here we're just displaying what kind of light should be shone on basil so that it grows better. And evolution discovered that basil doesn't need to sleep. You can have the lights on 24 hours and it will thrive. It becomes bigger and tastier. A huge surprise to the biologists. They thought that plants need to rest, like every one of us. But it turns out that they actually thrive in 24 hours. We would never have discovered that if evolution hadn't done it. Third example, this is something we built during the pandemic. A prediction model of how the cases will develop over the COVID-19 pandemic, with certain restrictions that the government will impose. Should they close the schools, workplaces, stay-at-home requirements, mask, contact tracing, various actions that can be done, how they affect the pandemic. And again, we have a prescriptive, predictive model that allows us to predict based on past history and past restrictions, and then make optimal recommendations. How can we keep the pandemic in check while at the same time economic impact at the minimum? If you're interested, there's an interactive demo where you can explore how things could have happened in the past. And it discovered things that we did not know. It first focused on schools and workplaces, and later predicted and would have mitigated the Delta surge if the government only had listened. But also it came up with creative solutions, like different restrictions on weekdays and weekends, agility, quick changes, and focus on certain dimensions. All right, so how can we trust the solutions? That's a lot of technology that goes into predicting the confidence intervals around the predictions, explaining them with rule sets, and also, even if the LLM, we can evaluate how confident we are with the LLM output. Last point, multi-agent coordination. We can build systems, multi-agent systems using these technologies, and they will result in better abilities in terms of flexibility and reliability. And later on, Dan Fink will give a short talk and hopefully also a demo of the system in the 4:30 session. All right, to conclude, decision-making agents are the future of AI. Neuroevolution discovers decision strategies, including creative solutions, useful solutions that you don't already know. And techniques that exist to make them trustworthy. And this, in the long term, should make AI-driven society possible in science, engineering, business, healthcare, other aspects, education, and so on. So there are lots of resources available if you're interested in diving deeper. We have a textbook or actual monograph coming out in a couple of weeks in HTML later at MIT Press in a physical form on neuroevolution. There's also a tutorial which has a video and slides, and much of this software is available open source, including the uncertainty and neuroscience system as well as the decision making. So that's it. Thank you.
Reinforcing reasoning. To train the agent, the goal is we want the agent to see, think, and act. So essentially, we try to use the reinforcement learning to see whether the agent can learn about how to reason in the environment. But if we check the current reinforcement learning algorithms, they have demonstrated the success in verifiable rewards, like trying to ask the model to do mathematical tasks or do the coding tasks. So these verifiable rewards can help the model to reason about which part is correct, which part is wrong. But if we move them to the real-world agency environment, it's much more challenging because the model is not just trying to learn from this single-turn reward, but actually they need to handle multi-turn feedback. And also, the state space explodes. So it's not just the finite problem set, but it actually can have multiple combinations of the states. Another thing is, it's not just the one single answer can help the model to decide whether it succeeds or not, but it's much more about multiple trajectories. Even if there's only the same goal, the model will try to predict the multiple trajectories to achieve it. So the environment part, we actually is not just trying to handle the environment that the model can fully observe, but a lot of cases, the model can only observe partially about the environment. All this actually makes the agent training much more challenging, and these challenges actually move us to this MDP, Markov decision process-based formulation for LLM agents. So there are two parties in this environment. One is mainly about the agent. Another thing is we want the agent to interact with the environment. So the agent firstly will take the goal from human instruction, and then the agent will observe the current environment to get the status, and then given the state and goal, the model trying to predict the action which will be executed in the environment, so we can get the next environment and the reward. So this actually will formulate as an MDP sequence that we have the states changes and the actions as a sequence. And then finally, we get the reward about a trajectory. So we propose this star PO algorithm to trying to capture this sequence-based learning that the model trying to learn from this state, thinking, action, reward-based sequence directly rather than just trying to predict a single answer. And to learn this, we actually ask the model to observe the entire trajectory to trying to get a cumulated reward to decide whether the trajectory is good or not. So we firstly ask the model to do rollout, and at each turn, we want the model to check the initial status and the current status, so the model can get the full historical history. And then the model trying to do the prediction based on all the historical context to decide like what they should perform in the next. And this thinking process will be also included in the thinking tokens. And then the action will be dispatched to the environment so we can get the feedback from the environment. This will finish the rollout stage, and this rollout stage will enable us to get some cumulated reward for the entire trajectory. And then after the rollout stage, we will have the update stage. So we just leverage multiple trajectories to see whether the model can learn from these trajectories about like which trajectory is correct. Surprisingly, if we directly apply this kind of multi-turn based trajectory learning using the RL algorithm, the model is actually not working. For example, if we just check the very simple environment like the bandit machine environment, Sokoban environment, frozen lake environment, you can see like the success rate firstly rise a little bit, and then it will drop dramatically to 0. It basically means like the model collapses. It's very surprising to us. So we are thinking like, why? What happens? If we look into this reasoning process, we actually identify the model will firstly, at the beginning of training, have a lot of diverse reasoning chains. And then when the model start to collapse, like at the turn 150, we can see like for several times, the model actually predicts exactly the same thinking tokens. So it basically means like there's some echo trap that the model just stuck into the locally optimized reasoning patterns, and they will not be able to really learn like from the trajectory which part of the trajectory is good and how they can make the good decision making. as a result, we try to monitor like how we can optimize this RL training process and trying to make sure the model can get converged, at least they can do a stable training. So we introduced these several monitor indicators like the reward variance and the like norm. When the norm gradient norm specs, the model will actually clap. So you can use this kind of monitor to decide whether the model get a good training or not. And then this, especially the output entropy, make us to realize like the model trying to identify the data that are really useful rather than using all the data. So compared to the left side to use all the data, we try to ask the model to select the data that are diverse and also informative. And this filtering strategy actually can make the model get much more stable training. And this contribute to the region training framework. And this kind of framework can make the model to learn to act. And the next thing is whether we can make the model to see. So the model will need to handle the multimodal states rather than the text states. For example, from the image on the left side, the model will need to verbalize them into either natural language or to the symbolic-based representation or some semi-structured representation like the JSON format. Essentially, this observation makes the model to change from the MDP process to POM-DP process, so partially observable MDP. And we can see the MDP process is basically trying to learn the word model from the current status. If there's an action, how can you change to the next status? And POM-DP actually introduced this observation stage. So the model will try to firstly get the observation and then do the state estimation, and then they do the state changes. We try to have this word modeling loss into the model training. So firstly, we ask the model to predict the current status, and then we ask the model to predict what will happen given this action. So this is the next state prediction. And this contributes to the vision algorithm, and all the algorithms actually are well formulated and welcome to play with our region and vision framework. And we can see, like, through this kind of training, the model is able to observe the environment and trying to predict what they will achieve after this action. And then we want to see, like, what the model really learned to see and whether this seeing part can be improved also using the RL training, like this kind of agent training process. So for this problem, we ask the model to check different views of the environment and trying to imagine what is in the view. So it's kind of like trying to construct a mental model. Like given the first view, the agent realized there's a door, and from the second view, they realize there's a desk, and then they realize after, behind the back there's a window, and if they change the view, there's a sofa on the right. So at the end, the model can construct a mental model about how the physical space is constructed, and then they can try to reason about the entire environment. So this is the man-cube environment. And then we ask the model to think in space by interacting with this environment and trying to get the feedback from the environment. And during the thinking, we ask the model to think over a map, like this cognitive map. And with this map and the reasoning process, this RL training algorithm can make the model have sufficient improvement. So we are thinking, basically, we want the model to not only to do reasoning, but also trying to learn better about how they can abstract this mental model from the environment. So this mental model is more like an interface. This interface is basically trying to connect the large language model with any environment. For example, we can build embodied agent interface, and we still build on top of this MDP framework. So we have this goal interpretation component and action sequencing component, sub-goal decomposition component, and also for the single step, we care about the transition modeling. And then we can construct a agent interface that contain all the important components so that they can connect the large language model with the agents. And if you are interested in this kind of direction, please feel free to check our tutorial about foundation models meet embodied agents. We use the MDP framework to connect all the related recent VLA and the VLM and LM agent work. Thank you.
So a lot of overlap with multi-agent systems. And so today I'll cover some of the learnings from all three of those experiences, and I'll also cover some of what we're doing at Mozilla AI to support open source AI, and I mean more than just models when I say open source AI, I mean the entire open source stack. And I'd love to talk offline as well about, do we include hardware in that stack? I think there's a real case to be made for trying to be as open as possible, as far as down as you can go in hardware, right? Like open up for TSMC, open up for ASML even, things like that. But first, okay, so I have a little bit of time for this talk. I was in classic professor mode last night, finishing up these slides, and I would like to summarize this talk in one slide, which was experienced by me yesterday, using a closed source system to do very basic research for this deck. So I just asked, completely new chat, what are some statistics about open source AI's impact on the economy, which was flagged by one of the frontier models, closed models, as violating their usage policy. Chatted with some friends at Hugging Face about this, and they said, hey, pass in some context about one of the responses we have for the recent Trump EO. So I've downloaded this PDF, I added in there, and I asked the same question. What are some statistics about open source AI's impact on the economy? Still flagged as a usage policy issue. Started arguing and saying, hey, why'd you flag this? Why'd you flag this? And eventually, this, well, now it is named, I guess, closed source system told me, hey, I made a mistake. Would you like me to start answering your question? To which I said, yes, please do, and it immediately flagged itself as a usage policy violation. So if you remember nothing else from this talk, this is one reason why we might want to have open source AI. It's so you can ask basic questions about open source AI's impact on the economy. Womp. So in this talk, I'd like to say that choice matters. Open source means choice, right? There's no one model or system to rule them all. And we do see, obviously, leaderboard chasing and new models being dropped, new systems being dropped with new state-of-the-art claims and so on. And I'm not arguing against that at all. These are incredible systems. But especially with multi-agent systems rising into being a real thing going into production, we're going to have more complexity in systems, more nuance in systems, more constraints that are put on these systems by maybe being on edge, having to be on-prem, different guardrailing and so on, different preferences from organizations, which means that there is no one-size-fits-all solution here. Okay, so choice is going to matter to the end user, that end user being those of us in this room who are primarily machine learning engineers, those being traditional software engineers, and those being just tech-curious folks who have never coded in their life. All of these three types of, say, ICP or whatever for your product are going to need choice. And some of this is also risk mitigation, right? You want to avoid vendor lock-in, right? For example, one frontier lab might turn off access to a frontier model that's very good at coding because of a potential acquisition by another frontier lab. That sort of thing can be mitigated with choice. So the thesis for this talk is that open source AI needs to be as easy to use as closed source to be a true competitor. So it's not just about model parity. It's not just even about system parity. It just needs to be about ease of use, where I can recommend easily to my mom or whatever to go to an actual open source system that she finds valuable as easily as she could with a ChatGPT. Great. So I do want to have some call outs to the open source world out here, and these are taken from Wiz, which did a large survey of the hosted instances for AI models and AI tooling across their customer base. And I believe these were just from like public hosting, so they didn't do anything sketchy here, but it's a very unique enterprise-focused population that they surveyed. And we can just start going down. The percentages here are the percentages of hosted instances in their customer base that were using, for example, the OpenAI SDK, about 2/3. PyTorch, about half. Onyx, about half. Hugging Face, about half. And so on and so on and so on is how you should read this chart. Okay? And part of what you can do if you squint here is you can see that open source AI tooling and models are being used at the enterprise, but often without much publicity. So I want to call out a couple things that I found surprising here. So this is the same data. It's just the top 10 most used AI tools or models on the enterprise side. And in gray, we have closed. In dashed pink, we have open-ish, like open-friendly, right? Like a TikToken from OpenAI is open-friendly. LangChain, I would say, is open-friendly. And then in full pink, we have full open source projects. And some easy things to pull out here are that 8 of the top 10 hosted technologies on the enterprise side are open source or open source adjacent. And there are things that you don't really hear about that surprise me. So for example, Mozilla has the LlamaFile project. And in nearly 1/3 of these hosted instances, Wiz was finding LlamaFile floating around. Okay, so this is clearly an enabler for enterprises. Enterprises have an easier time deploying open source AI. And maybe this comes as no surprise, but the numbers here, 8 out of 10, 32%, and so on, surprise me for sure. So we should be supporting this. There's clearly a need for it as well. So these are hosted solutions run by large companies. That is admittedly a very specific population. We're expecting AI to be used by every person on the planet, and so that is not just hosted solutions run by large companies. So again, coming back to this, open source AI needs to be as easy to use as closed source, more than just model parity, right? So if I don't have an IT team that can actually stand one of these things up and guardrail over it, I don't want to default to closed source by, just because it's harder for me to use. So, and you know, I'm not being a hypocrite here in the sense that I defaulted, you saw, to using ChatGPT and Perplexity while doing the basic research for the beginning of this talk, right? Because I was on crappy Wi-Fi, you know, I flew in, I was in my hotel, and they were easier to use than having to wait for a longer, you know, time to first token on my M2 MacBook on battery power. Okay, so, you know, I'm dogfooding my own thing here as well. So consumer and bottom-up adoption come through ease of use, being the easy default, and just generally not having to think about solutioning. Cool, so let's help make open source AI the easy default by developing tooling to allow blissful ignorance of the default, details by default. Very, very simple basic project that I'm just throwing out here because it's very easy to understand. One way that I can ignore the details of things, and I can just provide a single interface over components of the open source AI stack. Those could be models, those could be multi-agent system frameworks, those could be guardrails, those could be vector databases, those could be hardware solutions, and so on. So what my team at Mozilla AI has been doing, the things that we open source, and we open source these very quickly, is just spinning up projects that we find useful when developing our own product. For example, developing any LLM, which is just a light wrapper that gracefully handles differences in provider implementations for OpenAI standards, and then using them in our products ourselves as a way to maintain those projects and giving them out to the open source community. So this is dead simple to use. I have some comparisons against some other solutions that are out here that I'm happy to dive into a little bit. But basically, we built this because, you know, our internal teams were running into specific issues with known solutions that were out there. And we believe that we have a simple, easily maintainable solution for a very basic form of choice in this NELLM project, right? Not rocket science to develop a tool like this, but I think it's very important when it comes to, well, now I can flip out with 0 code changes an OpenAI model for a Mistral model, for a local model, et cetera, to do A/B testing, and then I can use that to do optimization over cost and so on, and I'm not just going to have to stick with, you know, I don't have vendor lock-in. I don't have vendor lock-in through my Python code base because I don't care about their implementation. I just have my own layer here to begin with. So comes as no surprise, very easy to use. This should look almost identical to, for example, the OpenAI SDK style coding that I'm sure many in this room have done. We have no proxies or gateways required, which is really, really great. And one of the reasons I'm excited about this kind of stuff is because it allows for easy A/B testing and easy evaluation of, in this case, different models behind the scenes without having to even know, for example, the name of the model. Moving on, you can, for example, do this sort of any style of approach with multi-agent frameworks. So we've heard a lot of people talking about multi-agent systems today. I'm very excited about it as well. They're starting to go into deployment. There are a lot of different frameworks that are coming out there, some open, some closed. And again, we're doing the same sort of thing with any agent here. So basically, it allows you to build and test and compare across different AI agent frameworks, the LangChains, the Crew AIs, you know, Hugging Faces, et cetera, without having to make code changes to your underlying code base when you do this. And so the community or Mozilla will take care of incorporating new frameworks as they come along, and then you as an end user don't have to care about that. So a big thing here is that we're also standardizing tracing formats across frameworks. I'm not in love with any of the single agent or multi-agent tracing methods that are out there right now, and a big credit to a lot of companies that are putting effort into this. Arise has open inference, OTel has a bunch of working groups on this. It's just a tricky problem. And so I'd love for folks to be more active in helping us understand what a standardized multi-agent tracing standard might look like so that we can continue doing standardized evaluation over different frameworks in general. So we also have A2A, MCP, and all the kind of things you would think about when you think about multi-agent systems integrated here. So again, very easy to use. Feel free to drop that QR code there. We have a bunch of cookbooks for this one that are available on the repo as well, because it's a little more complicated, right? Thinking about how you set up A2A integration or multi-agent systems with MCP enablement and so on. Yeah, this is a pretty cool project, which again, that we're using internally in our products, so it's going to stay maintained. So developing a bunch of these, all of them open source, not going to monetize them, all easy, commercially licensed in a nice way. I think they're mostly MIT licensed. We're going to be dropping any guardrails soon, which is going to allow you to seamlessly flip between different guardrailing products, both open and closed. And we'll be doing something similar with MCP servers and containerization around those. I could also imagine doing this with, again, vector databases and other forms of the AI stack, and we're happy to continue leading the charge on that. So supporting open source competitiveness is urgent now. For example, we saw Trump's AI action plan really highlighted open source and open weight models, which I think is very nice. The EU is having regulatory positioning around open source, some of this coming from the sovereign AI discussions around the DeepSeek moment, or whatever you want to call it. When you talk to policymakers on the West, they all seem to know the name DeepSeek. They might not know exactly what it means, but it is what they lead the conversation with. And so having a unified position from the open source community to talk about realistically the pros and cons of open sourcing models and systems, I think is very important for the future of the community. AI/ML usage is obviously increasing, and the potential gap between OSS and closed is increasing sometimes or not. I can argue back and forth on this, but there are some worries around, for example, some of the champions like Meta pulling back from their open source strategy and what that might mean for open source moving forward when it comes to capitalization. And finally, this is 2025. I'm giving this talk in early August. It's the year of AI becoming a thing in enterprises, thanks to agents primarily. So what do I mean by this? Well, in late 2022, prior to ChatGPT's launch, there was a lot of fear about a recession coming up. And so most enterprises set their budgets in October or November, and they froze IT for 2023. ChatGPT drops, and now CEOs and CFOs and the non-technical C-suite are able to interact with these systems. So they probably went home over their holidays and said, hey, I'm going to open up budget for this new cool tech thing. And in 2023, basically all of IT went toward where the only budget was, which was Gen AI. And so we had a lot of science projects in 2023. In 2024, we started seeing these going into deployment, and things started to go wrong. And then in 2025, evaluation started becoming a thing, and also agents started becoming a thing. So the reason I might say that 2025 is finally the year of evals and agents and AI is because up until then, we had, I don't know, ML models spitting out some numbers that were ingested in a larger system. And the only people who really cared about that were the CIO and maybe the CTO and maybe the CISO. It certainly was not the CEO and the CFO. So the ML part didn't really bubble up. The eval part didn't really bubble up to the highest levels, which meant that those years really weren't the big year for evals. But now we have agentic systems going into deployment. And what I mean by that, well, I'll use the traditional definition of agent here, the one from nerdy academia, which is an agent is going to be something that can perceive the world it's in, could be virtual, learn from its interactions with the world, abstract and generalize. So this is all like traditional ML models, and also reason and act. And so I have this highlighted in blue because this is truly what has flipped this year, which is we're allowing these systems to actually act either with lightweight human interaction or with no human interaction. And that introduces a lot of complexity and a lot of risk. Put another way, in 2025, we now have semi-autonomous systems acting for humans or teams of humans. Those systems are going into deployment, and the CEO and the CFO know what they are, which means this is the year where we're going to start seeing evals and open source tooling around that being top-level concerns for enterprises. So hold me honest here. Remind me in December 31st, 2025, the end of this year. Here are two articles from The Information talking about revenue lagging at AI evaluation startups. These are from earlier this year and from last month. I think we're going to see an article in 2026, early 2026, from The Information talking about how eval companies' revenue started going up. And I think it's because of this agentic system revolution that's happening right now. So to conclude here, this is an important year, right? We have AI-first applications finally going into production in enterprises. We have huge consumer usage from non-coders as well, who are going to have the wool pulled over their eyes in ways that a technical person might not. And we can't expect the users to know all the details all the time, but we can expect them to have their own needs and be able to express those. So let's continue to build open source AI tools to enable and serve them. And again, I'm going to end with this thesis over and over again, that we need to be focusing on the ease of use of open source AI if we want to have the community which now includes non-coders, right? It includes just tech-interested folks who are coding with natural language or whatever. If we want to have them included in the community, we have to be able to onboard them with ease of use. So I will conclude the talk with that. Feel free to take some QR codes, and we are actively hiring for SWE, DevRel, MLE, and I'm sure others that I'm forgetting about, so hit me up for that.
It's a great honor to share some of our recent research findings and interesting analysis about AI security, especially in the agentic world. And I'm Bo, the professor from UIUC and the CEO of Virtual AI. As some of you may know, at Virtual AI, we provide a unified AI security and compliance platform. So if you are interested in intern, or full-time, all the things, please contact us. Co-founded by many people you may know already, Dangsong, Sammy, Carlos, and me, myself. First of all, as we all know, from the research perspective, recently the models and agentic system, etc., has gone very quickly, and even out of our expectation. For instance, from the very important capability like reasoning itself, it has, based on the static benchmark currently, it has exceeded by like human expectation more than 90% accuracy. What does that even mean, right? It can enable a lot of capabilities in practice, including finance, chatbot, customer support, a lot of like practical applications. However, in this session, I think many of us care a lot about security, privacy, like compliance, etc. And let me give some examples from the real world, like what has happened and what loss has been generated and why we care about this and how severe it is, right? So maybe some of you have seen, like one of my favorite example is this back in 2016, the White House Associated Press Twitter account was hacked with phishing emails, spreading the rumor that the White House has been attacked, which is a very simple, typical, fake news, which can be easily picked up by human. But then the autonomous trading bot, as you can see, actually triggered a lot of stocks and purchase activities, and therefore swept about $136 billion within seconds, which exactly happens back in 2016. And now we're saying, okay, we have more and more, capable, like good foundational models, agent, etc. Well, such mistakes or like, I would say not very advanced attacks will still cause big loss in practice, right? As you can see, actually, some of you may still remember from last year, the Lyft price was jumped about like 30 to 50% within seconds, exactly because one digit typo in the annual report. So this shows that not only this like models and agents, they are capable. On the other hand, they open a much wider like vulnerability surface for attackers, for misuse, and even for normal users who can, draw mistakes and eventually could cause severe consequences. No mention, like as we all know, the chatbot output could be biased, could leak sensitive information, and could also give like hallucinated answer, like as we all know the example from Air Canada. With that being said, as we can see, it's very challenging currently to build the so-called secure and trustworthy AI systems. And we have been working very hard on that from all the communities, and a lot of regulations and policies have been built around that. But apparently, this is a very big topic, right? From security, privacy, compliance, from attacker, defender, guardrail perspective, right? So how do we think about this problem in a holistic view? So here in this talk, since we don't have a lot of time, I want to give a very high-level overview about the principles and about this topic so that we can think along a line, like maybe there are more or less components along the line, but at least we can join as a community to follow and focus on the principles. So first of all, let's say if we assume or if we take the AI system as simple as, say, a foundation model or agent, like enabled different, like say, finance, healthcare, autonomies, etc. And the first thing we need to understand the vulnerabilities and weakness of the system is through something like traditional pen testing or stress testing for cyber systems. And here we need red teaming and risk assessment for AI systems, including models, agent, multi-agent systems, etc. And the second piece is that assume we are able to provide like updated like vulnerabilities analysis, zero-day vulnerability identification effectively, etc. Then the second thing is, of course, we hope we can fundamentally fix the models or agents. And that being said, like reasoning, as well know, is very important capability, and how we can ensure current data-driven model can follow knowledge and follow reasoning capabilities. Although we talk a lot about the current emerging techniques and the capabilities of model with reasoning capability itself, but we know it's not really knowledge-based yet. Like we humans have common sense and we have reasoning over our experience in the past, but model is not there yet, unfortunately. So how we can ensure the knowledge-enabled safety reasoning to fundamentally fix a model through certain level of logical reasoning rather than only rely on purely data-driven models, that's another challenge. And finally, another thing is that basically, if the fundamental fixing the problem is hard, then how can we use them if we just want to quickly use the, somehow it doesn't show out, because this piece is important. Okay, so how can you quickly actually use it if we cannot fundamentally fix it right now, right? It's a long-term project, a long-term topic, as we can see. So the guardrail piece, I think many of you have heard about it, is very important, not only for models, for agent and the multi-agent systems, so that the guardrail itself can be an additional layer which can be tailored, could be a small model and could be capable, focused on this domain so that it can help and protect and separate the main capabilities and the security safety itself. So with that being said, here we'll show a quick video here as a vision, like assume we solve these three pieces as a principled way. And the first thing here is that assume we build an agent based on MCP protocol, for example. And there could be a lot of services and tools being available to choose. And here is a prompt injection attack that the agent will be attacked and send an email to the whole employee of the organization, but attach a malicious attachment here, as you can see, because of the prompt injection attack. So the idea of such protection is that it could be as easy as we add just another server itself as the agent guardrail, so that it can allow you to compose or select different safety, security rules, policies that you want to comply and follow. And then you just click run, and this agent or this guard agent, for example, should run in the background all the time to monitor every action steps and the trajectories of your current agentic systems to make sure they are secure and compliant. And therefore, in the end, for any action, such as the action that's attach the malicious attachment in the email, it violates certain security rules and policies. It will show you like, okay, this action is alerted because it violates these following policies. So in this way, it have this allow human in the loop to track the actions and also allow that in the background, the human do not have access to all the action trajectories, which is huge, high dimension and also long trajectories. And we leave all this to a trustworthy and task-focused agent guard itself. So that's a vision for if we address everything, right? This is a prototype we built, and this is a paper that we'll introduce later. But essentially, this can be integrated, hopefully, to every different platform. For example, this is an example of an open source platform called Flow, and allow you to build different types of agentic systems. And with this being said, in this video, we want to quickly show that this is a relatively complex agentic workflow that we build for finance agent, and then eventually here will be the prompt injection attack and showing that I want to buy a stock and I want to consider buy Apple stock, for example, unfortunately. And then if you run this agent, no matter what you tell, no matter what information from online for this a stock price comparison you give, since the agent is attacked, it will always access this attack itself and execute it, so that once you run the agent will always recommend you and actually execute it for you to buy the stock from Apple itself. So the idea similar is that can we add as simple as a virtual agent here, for example, to perform such guardrail task so that you can configure all the things like say what policies, and again here in the dashboard in terms of what policy to add, what policy to remove and comply, with flexible customization, and then you can just go back and connect it as another tool or server. That's all, right? And then you can easily just focus on your agentic system capabilities and innovations, do whatever you want, and you don't need to worry too much. And in the end, if some actions or instructions are triggered or a malicious intention, this agent will tell you, okay, there is something, and here as a policy violation, please check it, and it should be alerted, right? And it will also eventually give you statistics about what policy is highly likely to be violated and what actions are highly vulnerable currently, so you should pay attention, and you can check out a lot of details here. So hopefully that gives us a high-level overview about what we, at least from our mission, from both research and the startup perspective, what we eventually want to achieve, so that a lot of AI researchers for us can focus on our capability and innovations and leave the security part with our focused research and focused model and continue to build it. So with that being said, the two videos shows prototype and vision, and concretely how we can achieve that and what's the obstacles from the research and from the methodology perspective. So I will briefly introduce those, and basically mainly on the principle level, and happy to discuss more details offline. So remember the three pieces, like risk assessment, fundamentally fix the agent or models, and a quick fix with additional component like a guardrail, for example. First, in terms of risk assessment, right? The main research question or the main challenge we face now is how do we assess the risks of models and agents in a principled way? For example, what's the perspectives we want to focus, right? Currently, we have seen a lot like a privacy leakage, hallucination, and of course, like bias and fairness, all these things on weapon, and how do we articulate them? What's the principle behind it, right? So currently, we focus on two principles. Maybe there are more, but I think as a community, we can develop together, hopefully. And the first principle is use case driven. So use case driven means that maybe some of you are familiar with this paper, Decoding Trust, which is also the best paper from NeurIPS and like a national security agency. So basically, the idea is that based on use case itself, we can articulate different risk categories, including like toxicity, stereotype, bias, adversary robustness, OOD robustness, etc., so that you can focus on those risk categories and, of course, like sub-scenarios and advanced attack algorithms. So with this being said, you will provide a comprehensive risk assessment for LM, for multimodal here, for like agents, and then we also provide this like a Hugging Face hosted LM safety leaderboard based on the platform. And the second principle is like regulatory compliance risk analysis. So basically, as we know, use case is one hand in real life. On the other hand, there are a lot of policies, regulations, etc. How we can ensure like our model and agents are following those, regulation policies for general use cases. This is very important. And with this, we have this one research called AIR, AIR, and also integrated with Stanford Helm leaderboard, continues to update the models and also include many different regulations, including like EU Act, GDPR, etc., and articulate more than 300 risk categories so that we can focus. So I think hopefully this could be a helpful pointer for everyone to look into the risk assessment itself. And with that being said, I want to quickly go to the agentic system side for the guardrail so that we can focus on after the risk assessment. The next piece is fundamentally fixing it, which will take a longer time. So I will skip here, but I think many of us are interested here in guardrail itself, right? Because it's an efficient and quick and also effective solution for many of the, say, the models and agents you have built. For example, from the startup world, like one experience I have, which is really interesting, is that I talked to one customer and they said they have built hundreds of chatbots, but they cannot deploy any of them because of the security privacy concern, as you can imagine. So how, as research and as a community, we can help them and, fill in this critical last mile so that those like very capable agents and models and chatbot can be deployed with trustworthiness and the secure insurance. So that's what we want to focus here. So one thing from the guardrail perspective is that I want to quickly mention this is one paper, Shield Agent, and if you're interested, you can take a look. It's related to the demo that I just showed. It's like prototype and early stage for that. And there are several components. I want to use 1 minute to go through it because I do think it's very important. First is that risks. We need the guardrail model, whatever guardrail agent, to understand the risk landscape, right? How do we do that? Of course, the current models can have comprehension about, NLP, about rules, etc. So here we provide all the regulations and policies as an input to the model. Nothing special, right? That's good. But as we know, models sometimes will hallucinate, and you cannot never ensure it follow or not about your models and the rules and the policy, etc. Therefore, the second step is very important, is that we articulate this, safety rules and policies as, say, higher order or first order instructions or rules, so that this higher order logic itself ensures the model can follow the logics for the safety reasoning itself. And eventually, we ensure, map these different safety rules as a, say, an action graph, and the action graph can ensure the models to follow it, and then you can do actually verifications, model checking, everything, etc. So here will be with action graph, you can do a lot of, checking, guardrail with formal verification, and you can integrate with different agent, MCP, A2A with different protocols, etc. So with that being said, just a quick summary of this talk is that 30 years ago, basically we have a map like this, and our computer looked like this, like time flies, right? And there was a paper called like this. And after 30 years, as we can see from the internet perspective, everywhere, like no one currently do not have internet access, right? However, similarly for Gen AI technology like ChatGPT, for example, this is recently this year, like the statistic of where are the regions who have the access to ChatGPT and Gen AI techniques itself. But as we mentioned, it's very challenging currently as a critical last mile to ensure those techniques are secure and trustworthy so that it can be deployed. So whether we can see, I would say, a wide adoption like internet for our Gen AI technology, it highly depends on how secure and how trustworthy we can make them, right? Don't know what will happen, and this right-hand side figure is actually hallucinated by GPT models and say, oh, this could be the future. But we'll see. Yeah, hopefully, as a community, we can build the secure and trust AI together. Thank you.